Hey folks, today we are going to build this plugin from scratch using modern C++ and the JUCE framework in this free course. Check the description for links to the repository and to download the final build. Okay, what is this thing? This is the little brother of this other plugin, which is my new course for PFM C++ for musicians, which is where you can build this other plugin, which is also where you can learn modern C++ and the JUCE framework from scratch, taught from the context of writing audio software in a mentored environment. You're not following videos, you're not watching someone else code, and you're not copying them. You're coding it yourself, and I'm reviewing your work. All right, enough about those. Let's learn about what we are going to build today. This is a 3-band equalizer with a spectrum analyzer at the top. It has a low-cut band, it has a high-cut band, and it has a parametric band in the middle. The low-cut band lets you cut out all of the low end of the signal. You can also control the steepness of the cut. The high-cut band lets you remove all of the high frequencies, and you can also control how steep that cut is. The parametric band lets you add notches or boosts, and we can also control how wide or how narrow those boosts are, and we can control the frequency. Everybody's familiar with this type of swept frequency sound. Above that, there are bypass buttons, which allow you to disable individual bands, which is always helpful when you're working on audio. Then above that is the response curve, which gives us a visual representation of what the filters are doing. Then behind that is the spectrum analyzer, and this shows us what we are hearing. And these always use a bunch of CPUs, so there's a bypass button for that as well. We're going to learn all the DSP that's going on in the background that makes this thing work. We're going to learn how to draw everything, how to draw the sliders, the bypass buttons, how to draw the response curve and make it respond whenever we adjust the sliders, and how to draw the spectrum analyzer. Okay, that's the feature set for this plugin and for this free course. My name is Chuck. I go by the name MattCatMusic on YouTube and Instagram. Once again, check the description for links to the repository and to download the final build of this plugin. So let's get started and write some audio software using modern C++ and the JUCE framework from scratch. All right, the first thing we need to do is get set up with the JUCE framework. Now, if you've never done any audio programming before, fear not. The only things you need are two tools, the JUCE framework and then an IDE to write code in. That could be Xcode or it could be Visual Studio. It depends on what operating system you're running. I'm on Mac, so I'm going to be using Xcode for this video. If you've never set yourself up with an IDE before, I have 2 videos linked in the description. They take you through the process of setting up your computer with an IDE, getting the JUCE framework, setting up Producer, setting up a Git repository, making your first project, and then pushing changes to that. And it basically gets you familiar with the flow, with the workflow that goes in with being a software developer in the context of writing audio software. Okay, so the first thing we're going to do is go get the JUCE framework. So let's do that right now. I'm going to open up Safari, because that's this is like just a blank OS install, and I'm going to install, going to grab JUCE. So JUCE Framework, just going to search for it. It is hosted on GitHub. So I'm going to go grab it here. Now what I'm going to do is I'm going to clone the repository. And the reason is because this is an active repository. They make a lot of changes to it, okay? So especially on the develop branch, we want to make sure that we have all of these changes because stuff's getting fixed all the time. Features are being added, that sort of thing. So if I have the repository cloned, I'm able to pull in those changes. This is different from if I had just downloaded a zip file. So that's why I'm going to do that. Okay, I'm going to go to Terminal. If you don't have Terminal open, just, Terminal, open it like that, or open some kind of command prompt shell. Okay, then I'm going to, let's see, I've got my users folder right here, and I'm just going to clone the repository right into that. So git clone, and then the URL. Just like that. That's going to make the JUCE folder, and it's going to download this repository into this folder, and it's going to include all of the commit changes as well. So let's just wait for this to finish. All right, there it goes. There's the JUCE framework. Now, what we want to do is switch to the develop branch because, as I had shown, it is it contains more recent changes than the other branch. You can see that the develop branch is 19 commits ahead of the master branch. So to do that, we need to type in terminal. First, we need to go into the JUCE folder. So let's do that right now. cd juice /juice. And now we need to do git checkout develop, like that. All right, switch to a new branch, develop. Okay, cool. Now, I prefer to use a git GUI, so I'm going to be using fork from now on in the course of this simple EQ that we will be building. So I'm going to open that now so we can see what this repository looks like in that sense. So I'm going to open up fork. Fork is available from fork.dev. Okay, so here is the repository. I had already added it previously. And you can see here's all the commits that have been added and all the basically all the work that they've been doing on it. And you can see how frequently they update the develop branch. Okay, our next job is to open up ProJuicer and use ProJuicer to make a project. ProJuicer is found in the extras folder inside ProJuicer. Now inside here, you're going to find a builds folder, and in there is a project file for each operating system. You got Linux, you got Mac, and you got Windows. So if you're on Windows, open the solution file, depending on which version of Visual Studio you're running. If you're on Mac, you're going to open up the Xcode file. If you're on Linux, there's a make file, and you Linux users know what to do with make files. So I'm not going to talk about that. Okay, I'm going to open up ProJuicer, the solution file. That's going to open up Xcode. And now all I need to do is just build and run. Okay, so we just need to wait for this to happen. Apologies if I start speaking fast. I like doing this stuff a lot, and when I get excited, I start to speak really fast. So if I happen to speak too fast, I'm probably going to take a step back and repeat what I say slower. So just apologies in advance if I start speaking really, really fast. All right, so let's wait for this to finish building. Build succeeded. Now it's going to run it, and then we will be able to configure this stuff. All right, so let's get this set up. Okay, we are presented with the new project wizard. Before we do that, we want to go to ProJuicer and we want to configure our global paths. And these need to point to the JUCE folder and the modules folder. Now the JUCE folder, by default, if you clone the repository to your users folder, this stuff is going to be set automatically. It's going to go right to your users folder and then a JUCE thing. However, if you decide to put it somewhere else, you need to customize these modules. So click on this button right here, and then navigate to wherever your JUCE folder is stored for setting the path to JUCE. Then do the same thing for the modules. Click that button, navigate to your JUCE folder, and then navigate to the modules button, to the modules folder inside of that. Okay, and then if you rescan, it'll tell you if there's any issues or not. Once that is done, now you can go to the plugin right here, basic, and we're going to create a project called Simple EQ. And then we can do create project, and it's going to ask me, where do I want to save this? Create project. I want to save it to this programming folder. And there it goes. It's going to save it. It's going to make it. And now if I reveal in Finder, here is my project. So I am going to make a Git repository next before I actually take a look around at the code, because it's always important to set yourself up with the Git repository in case you have to backtrack and undo some stuff or whatnot. So I'm going to do that next. All right, so in the interest of keeping everything neutral, I will not be creating the repository in fork, but I will be doing it in terminal because everybody's computer has a shell. It may not have fork in it. So what I need to do is first navigate to the folder that my repository is in. So I'm going to do that. CD, I'm just going to drag this folder in here. Now I'm inside that folder, and now I'm going to do git init, like that. Okay. Now I'm not seeing it, so I'm going to turn on hidden files. And now here is my Git repository. Okay. So what I need to do next is create a, I need to do an initial commit and commit the state of this. Now I do not want to include everything that's in this builds folder, and I do not want to include everything that's in this JUCE library folder, because JUCE library code folder, because every time we resave this ProJuicer file, it recreates these folders. The only thing we want to keep is the juicer file and the source file. So I'm going to add a git init file first, or a git ignore file, sorry. So I will do touch.git ignore, like that. that creates a document which I can open with a text editor and specify that I want to exclude this builds folder and this JUCE library code. So let me go do that. I'm going to open this with, I can open it with text edit. That's fine. And I want to write / builds with caps / JUCE library code. Okay, that's the name of these two folders. And then because this is OSX, I'm going to do //.ds_store like that. We're not seeing any of those files right now, but sometimes we will. That's basically if I configure how this folder looks, it's going to get stored as a DS store file. And those are super annoying to include in your repository, so it's very good to keep them excluded. Okay, next I'm going to do git, git commit -m. This is my initial commit. Let's do a git status first. Let's see what we got. Git status. We can see that there are no tracked files, so let's add our files. Git add. And you'll notice that it's the untracked files does not include anything in the builds folder and the JUCE library code folder. And that's because of the git ignore file. It's doing its job. Let me just move this out of here so you can see what I'm talking about. So if I do that again, let's see. Let's do git status. We can see we've got these new files here, but it's also not tracking these guys. So there is a DS store somewhere. There's a builds folder and there's a JUCE library code. Okay, as I said before, we don't want those included, so I'm going to put that back. And then we'll do git status one more time. Okay, so we've got our git ignore, the juicer file, and then the 4 source code files. All right, now that we have those ready to be committed, let's make a commit. Git commit -m initial commit. Whoops, I forgot the closing quote. All right, that's fine. Good enough. Okay, now I can open this in fork. I can do file, open repository. So now I can actually see what's going on. And here's my initial commit. All right, good times. Okay, so if we want, we can go make a repository on GitHub and push the code there, or just keep it local. But either way, now we can keep track of everything. Okay, so I'm going to give you a quick overview of where everything happens in the source code now, before we actually start work on this. Okay, so this is going to be a brief overview of how these plugins work and where we will primarily be spending most of our time doing edits in the code. So we have 4 source files right here. We've got pluginprocessor.cpp, pluginprocessor.h, plugineditor.cpp, and plugineditor.h. Let me pull up the assistant editor so that we can see what's going on both sides. Okay, pluginprocessor.h. In a JUCE plugin, you've got 2 main functions that are the most important. There's your prepare to play function, and then there is your process block function. Prepare to play gets called by the host when it's about to start playback. And then process block is actually what happens whenever you hit the play button in the transport control. When you hit that play button, the host just starts sending buffers at a regular rate into your plugin, and it's your plugin's job to give it back any finished audio that it is done processing. You cannot interrupt that chain of events. If you add latency or whatever, it can cause clicks and pops in your speakers, and that has the potential to damage speakers as well as explode eardrums. Just imagine this scenario that you're at a club and the sound system is super loud and your plugin causes a pop or a glitch, and the sound engineer or the DJ or whatever has their thing totally cranked, and there's just this huge pop and everybody's ears just go psh, like that. So that's why that's the big thing about audio processing is you can't interrupt this process block and anything that goes on inside it. You have to just kind of you got to figure out how to get all the work that you need done by your code done within a fixed amount of time. Okay, so those are the 2 big functions we were going to be spending most of our time with: prepare to play and then process block. Now, let's take a look at what happens over there. So in prepare to play, use this as the place to do any pre-playback initialization that you need. And then in process block, this is where you get your actual block of audio data. And if you're using a MIDI controller, these are where the MIDI messages are. But basically, this is where we do all of the work. We're going to be typing all a bunch of code here, and we have to make sure that it doesn't happen in like more time than we have been allotted. Okay, let's go take a look at Plugin Editor. Now, Plugin Editor is where we set up all of our visual elements, and there's some basic stuff. You got your basic constructor, you got your paint function, your resized function. Painting, you know, it's what we're going to see. Right now we're showing a hello world. If I run this real quick. So before I get into showing how to run it, yeah, right now we're just going to see a hello world displayed at the center of the screen. And then if we have any child components like buttons or subcomponents or anything like that, we'll lay them out here in the resized function. Okay, so that's a basic overview. We're going to be basically making child components to represent the knobs and the sliders and the spectrum analyzer and the response curve, and then we're going to be, you know, drawing them in there based on some, you know, audio parameters that we've got. Okay, so let's run this for the first time. What we need to do is go to our particular scheme. We have a few targets. We've got a VST3 format. We have an audio unit format if we are on OS X, and then we have the standalone version. Okay. So I'm going to put this on standalone. In Visual Studio, you'll do something similar. You will set the target to run to be the standalone version. And then all we need to do is just run it. Build and run. It's going to compile these 4 files. It's going to compile any module files that are being used. All right, here's our standard plugin. It's not doing anything. It's just displaying hello world, but it is processing audio. So yeah, that's it. There's our basic plugin. We're going to turn this into the thing I showed at the very beginning. I wanted to add a quick note right before we get started writing actual code. What you need to do is go to Producer, click on this gear right now for the project, click on this gear, scroll down, and you need to change the language type to be C++ 17. Okay, a lot of the stuff we're going to be using this involves C++ 17. Okay, once you've done that, just click Save and open an IDE. All right, let's start coding. Navigate to the audio, to the plugin processor.h file, because we need to declare some variables. Audio plugins depend on parameters to control the various parts of the DSP. JUCE uses an object called the audio processor value tree state to coordinate syncing these parameters with the knobs on the GUI and the variables in the DSP. So we need one of these in our audio processor, and it needs to be public so the GUI can attach all of its knobs and sliders and buttons and combo boxes and stuff to it. All right, so let's declare one of those. All right, we need to give it a name. I'm just going to call it APVTS. And then we need to make sure that we use curly braces here, not parentheses when we declare it. All right, the audio processor to connect to is going to be this audio processor. We are not going to use an undo manager. We're going to just call it parameters. And then we need to provide a function here to give us a parameter layout. So the APVTS expects us to provide the list of all parameters when it is created. So we need a function that will provide that for us in the form of an APVTS parameter layout. So let's create that now. All right, and we can just call it. And actually, let's make it static, since it doesn't use any member variables. I have an extra colon. Okay. Let's declare this guy right here. Now for this project, we will keep the DSP and the GUI simple. We are only going to have 3 equalizer bands: low cut, high cut, and peak. For the low cut and high cut bands, we will be able to control the frequency cutoff as well as the slope of the cutoff. For the peak or parametric band, we will be able to control the center frequency, the gain, and the quality, meaning how narrow or how wide the peak is. All right, so we will start with the low cut and high cut frequency parameters. And JUCE has an audio processor parameter class. And let me pull up the documentation for this real quick, actually. All right, so JUCE has an audio processor parameter class. This class is a generic interface towards all the different audio parameter formats that different plugin hosts use. For example, audio unit on OS X is used by apps like Logic or Final Cut or GarageBand. VST3 on Windows and OS X is used in apps like Cubase or Ableton Live, Reaper, or Bitwig. And then there's AAX for Pro Tools. Okay, now the audio processor parameter class has several derived types that represent things like sliders and switches and combo boxes. And for our needs, the audio parameter float type is used to represent parameters that should be represented on the GUI with a slider of some kind. So we want our frequency range to be adjustable over a wide range, so we are going to use an audio parameter float for this. So let's declare one of these. And I hope the font is big enough for you to be able to see what's going on. We're going to return our layout. And now we can add an audio parameter float to this. So layout dot, let's see, add. And these things want unique pointers, so we'll use make unique for this. Make unique. And we want a JUCE audio parameter float. We want that guy. All right, the name of this is going to be LowCut Freak. The parameter name will also be LowCut Freak. The normalizable range is the next part. Now, the human ear has a range of roughly, it can pick up sounds from 20 hertz to 20,000 hertz. So that will define the range for our parameter. Let's create one of these. Whoops. Normalizable range. Where's the one that takes parameters? This is the one that we want. Okay. We're going to make it use type float. Okay, now the range start is going to be 20, and the range end is going to be 20,000. Now the interval value, we're going to use a interval value of 1, and what that means is that our slider will change the parameter's value in steps of 1. We could use bigger steps if we wanted to. For example, we could drag the slider. If this was set to 10, then our slider would go from like 20 to 30 to 40 to 50 every time we dragged it. But as we get in the upper range of frequencies, that could be helpful. But in this lower range, the audible effects of like 20 hertz versus 25 hertz, like they sound like different notes on the piano, whereas 2000 to 2050 does not really sound like different notes on a piano. So we're going to keep this at a step size of 1. Okay, the skew factor. Now the skew parameter lets us change how the slider responds. What that means is that we can skew the slider such that the majority of our mouse movements are covering the lower part of this parameter's range. For example, I'm reading my notes over here. For example, I could set this skew value such that 75% of the slider's range covers the values 20 hertz through 1000 hertz, leaving the last 25% of the slider's range to cover the remaining frequencies, 1001 hertz to 20,000 hertz. Or I could skew it differently so that the slider's bottom 10% covers from 20 hertz to 1000 hertz, and the remaining 90% of the slider's range covers 1001 hertz to 20,000 hertz. And since I don't want to be doing any skewing right now, I'm going to leave this set to 1. All right, and then the last thing is that the default value for this parameter. Now this is the LowCut parameter, so we will give it a default value of 20 hertz. Because that's the bottom of the hearing range, and we don't want to hear this parameter do anything unless we actually move it. All right, so that takes care of the LowCut parameter. Let me hide this plugin processor and just show the plugin thing, so you can see the full name of this guy right here. All right, we've got our name, we've got our parameter name, and then we got our normalizable range right here, and this is our default value. We are going to do the same thing with the high cut frequency. The only difference will be that we will set the default value to 20,000 hertz because it's at the top of the human hearing range, and we don't want to hear this parameter do anything unless we decide to change the value. So I'm just going to copy this. I'm going to change the name to high cut, and then this needs to be 20,000. Now let's do the same thing for the peak frequency. We will use the same range of 20 hertz to 20,000 hertz. The same step size of 1 and the same skew value of 1. The only difference is we will set the center frequency to a default of 750 hertz. And let's change the name to peak. For the peak gain, we will be expressing this parameter in decibels. And a good range of values to use here is -24 to +24. A step size of 0.5 means that when we drag the slider back and forth, it will represent a change of half of a decibel. And we want this slider to behave in a linear fashion, so we will use a skew of 1. And we don't want this to, by default, add any sort of gain or cut, so we're going to use a default value of 0. So I'm going to copy this. We're going to change the name to peak gain. The range is going to be -24.f with a max of 24.f. Our step size, 0.5f. Our skew of 1, and our default value of 0.0f. Okay, that's our gain. Next, the peak band's quality control. The quality controls how tight or how wide the peak band is. This is kind of an abstract number and it doesn't have any units. You can have a pretty narrow Q, which is reflected by having a high Q value, or you can have a very wide Q, which is reflected by having a very low Q value. So let's give ourselves a low value of 0.1 and a high value of 10. Well, I'm going to copy this. Let's copy this parameter. Change this to quality. Change that to quality. So we will, so we're going to give it a low value of 0.1 and a high value of 10. I'm going to use a step size of 0.05, which means when we drag the slider, it's going to go 0.1, 0.15, 0.2. These can be pretty granular sizes, which means we can have a lot of control, which is good. And always we want a linear response, so we will set the skew on this to 1. And on top of it, we want to use a generic default value of 1 for the Q, 1.f. All right, for the low cut and high cut filters, I want to have the ability to change the steepness of the filter cut. So I will give myself some 4 different options. Okay, our cut filters are normally expressed in decibels per octaves, or their responses are normally expressed in decibels per octaves. Sorry, the way the math behind the filter equations works ends up expressing these choices in multiples of 6 or 12. So that means we can have choices like 12 decibels per octave, 24, 36. So for this project, we're going to stick with 4 choices, 12, 24, 36, 48. So because we are using specific choices and not a range of values like with these sliders, this means we get to use the audio parameter choice object. So I'll show you what that's like. Audio parameter choice. So that's this thing right here. This thing, it needs a string array that represents the choices. And because both the low cut and high cut will use the same set of choices, I only need to create this string array once. So we're going to do that first. Let me get rid of this line. Let me scroll up. Okay, so let's make our string array. And now we're going to do 4 choices. And now we are going to construct something that says 12 dB per oct or 24. And we can do that like this. All right, that should make a lot of sense. Default value is 0. So we've got, i's first value is 0. So we've got 12 plus 0, then 12 plus 12, 12 plus 24, 12 plus 36. That gives us 12, 24, 36, 48. And then we're just sticking dB per octave on the end of that string. All right, now we just need to create the audio parameter choice and give it the string array of choices and use the default value of 0, meaning the filter will have a default slope of 12 dB per octave. Let's create that now. This is going to be called low cut slope. Choice is going to be our string array. And our default index will be 0. All right, and we just need to duplicate this line for the high cut as well. All right, now we have got our parameters set up in our parameter layout, so we can just return it and pass it to the audio processor tree value state constructor, which we have already done. We already did that right here. All right, now if we run the app as it is right now, we are not going to see anything other than that hello world. And that's because we haven't added anything to our GUI. But if I go up to the create editor function, we can use the generic audio processor editor to see what our parameters look like. So let's do that. We're going to comment that line out. We're going to write return new generic audio processor editor, and it's going to be this. Okay, so if we run it and take a look, First of all, make sure you are in standalone mode. If we run it, we are going to see some good stuff. Okay, if we look at our combo boxes, we can see that our slope controls show up this way. Here's our 12, 24, 36, and 48. Peak control, default value of 1. We can see it goes, 0.1, 1.5, 2.5, all the way up to 10. And then for our gain, we got 24. We can see that it's stepping by half of a decibel every time. Okay, so next we will work on the signal processing side of things. That's the next step, to make all these parameters actually do something. All right, we've got some parameters set up now. This would be a good time to make a commit and, commit what we've done. So that way, if what we do in the next step gets messed up, we can always revert back to here and try again. So added parameters, we can see what we did. We created the audio processor value tree state, created the parameter layout. Then we added our parameters and made it give us the generic audio processor editor whenever we go to look at stuff. And then we also changed the language to C++ 17 and did an export for, in my case, OS X. In your case, it's probably for perhaps it's OS X or Windows. Anyway, we'll add those things, stage those, and make a commit. All right, so next thing we're going to do is add some DSP. Now, before we do that, before we actually start writing DSP code, we need to add the DSP module. So go to ProJuicer, click on the modules thing right here, then click the plus button, and you're going to do add a module, global juice paths, and go to JUCE DSP. All right, once that is in there, then we can click on this guy. And now we have access to all of the JUCE DSP modules. Okay, I'm going to switch back to the single view for right now. So let me hide this and then go back to pluginprocessor.h. Back to my script. If you have never written any audio software before or used any type of audio software, then you might not be familiar with the concept of audio channels and stereo versus mono audio. So stereo means there's two channels, mono means there's only one. Now, each of the signal processing classes in the DSP namespace is set up to process mono audio, unless it's declared as stereo in the documentation. So what that means is that it's only going to process a single channel of audio. And since this plugin is going to be processing stereo audio, we need to duplicate all of the stuff we are going to use. And the DSP namespace uses a lot of template metaprogramming and nested namespaces. So let's help ourselves out. Let's create some type aliases to eliminate a lot of those namespace and template definitions. First thing we are going to create is a filter alias. We're going to be processing floats and not doubles in this project. That's our first alias. Now, I said before how we can set the slope of our cut filters to be multiples of 12. Each of the filter types in the IIR filter class has a response of 12 dB per octave when it is configured as a low pass or high pass filter. So if we want to have a chain with a response of 48 decibels per octave, we are going to need 4 of those filters. Now, a central concept of the DSP namespace in the JUCE framework is to define a chain and then pass in a processing context. That's an important term. Pass in a processing context which will run through each element of the chain automatically. So we can put 4 of these filters in a processor chain, which will allow us to pass it a single context and have it process all of the audio automatically. So let's do that. Using cut filter equals processor chain. And then this is where we do 1 filter, 2 filter, 3 filter, 4 filter. As I mentioned earlier, if you configure the filter as low pass or high pass, it will have a 12 dB per octave slope. We can also configure that filter to work as a peak filter or shelf or notch or band pass or all pass. There's a couple other types. This means we can use one of these filters to represent the parametric filter. So now that we have the peak filter and the cut filters represented as aliases, we can define a chain to represent the whole mono signal path. So we'll do that using mono chain equals JUCE DSP processor chain. And then we will do a cut filter, then a normal filter, and then a cut filter. Now we need 2 instances of this mono chain if we want to do stereo processing, and to have access to the filter instances in order to adjust their cutoff, gain, quality, or slope. So let's declare that now. Mono chain. We got the left channel and the right channel. Cool. Now before we can use our filter chains, we need to prepare them. So let's go over to our prepare to play and do that. We must prepare our filters before we use them, and we do this by passing a process spec object to the chains, which will then pass it to each link in the chain. So let's declare one of those. And it needs to know the maximum number of samples that it will process at one time. It needs to know the number of channels. Mono chains can only handle 1 channel of audio. And it needs to know the sample rate. Now we can pass it to each chain and they will be prepared and ready for processing. And let's just make sure everything's cool and build it. Build succeeded. Okay, step number 3. This requires us to jump down to our process block. Now the processor chain requires a processing context to be passed to it in order to run the audio through the links in the chain. In order to make a processing context, we need to supply it with an audio block instance. Now the process block function is called by the host, and it is given a buffer which can have any number of channels. So we need to extract the left channel and the right channel from this buffer. And the left and right channels are typically channels 0 and 1 respectively. So the first thing we have to do is create an audio block which wraps this buffer. So let's do that first. We're going to get rid of this stuff right here. All right, this is a block and it is initialized with our buffer. Now we can use the helper function in the audio block class to extract individual channels from the buffer, which will then be wrapped inside more audio blocks. So we can do auto left block equals block.get single channel block. We want channel 0. Do the same thing for the right channel. Now that we have audio blocks representing each individual channel, we can create processing contexts that wrap each individual audio block for the channels. Process context replacing, it's a float. We're going to call it the left context. It's going to be initialized with the left block. Make another one. All right, so we have our block representing an individual channel. We have a context that kind of provides a wrapper around that block that the chain can use. Now we can pass these contexts to our mono filter chains. Left chain dot process, and we want the left context, and then right chain dot process, right context. Now if we run it, it will work, but we will not hear our filters do anything because we have not set up their coefficients. So this is going to be a good time to set up the audio plugin host so we can feed some actual audio through our plugin and show that the filters are not doing anything. But until then, we can actually just run this and you'll see that it's not going to do anything. Cool. So we can drag all this stuff. There's no audio running through it, so we're not going to hear it do anything. Okay, let's get set up with audio plugin host. This comes with JUCE. Navigate to your JUCE folder and then go to extras and now go to audio plugin host and now open the you can open the juicer file if you want. I'll do that. Now I've got this here. It's just like the other thing where we have all our source and our modules and whatnot. So all we're going to do is just save and open in IDE. Wait for this to open. And now we just need to build it. All right, build succeeded. So we are done with this project now. That was very easy. Okay, what we have to do now is run it outside of our project. So go to the builds folder, go to your particular operating system. I'm going to go to Mac OS. Go to build, debug, and now run it. All right. It's going to want access to whatever device you have. What we have to do now is scan our system for the plugin. I haven't built it yet. I've only built the standalone version. So I'm going to change this to all, and I'm going to build it now. And what it's going to do is it's going to create a VST3. It's going to create an audio unit, and it's going to copy them to the relevant locations on the computer. Now I can go back to Audio Plugin Host, and now I can go to the Options menu and edit the list of available plugins. And now under this Options button here, this is where you're going to scan for both, if you're on Mac, audio unit and VST3. So we'll do VST3 first. It's going to find our simple EQ because we built it that way. And then for audio unit, do the same thing. In my case, I have a bunch of UAD stuff, so it's going to find all of that. Okay, so now that we have all of our audio units that are built into the computer and our VST3, close this available plugins list window. Now we can right-click right here, go to the your company, unless you put something else in, and pick VST3 for right now. Here's our plugin. So that's good times. Now we want to run some audio through it. So what we want to do is right-click here. On OS X, you're going to go to the Apple menu. You're going to go to the AU audio file player. Now this little plugin lets us load files and play them. We can load sound files and then play them. So we're going to wire this up, connect it to our audio output, and then be able to hear audio running through our plugin. So just drag like this and drag that to our audio output. And then, the other thing to do is you need to make sure that under your options, go to your audio device settings. And this is where you're going to configure your audio on what you have. Now I'm going to set this up with an audio file that I have. Feel free to set it up with your own. I'm just pulling something that I got from YouTube's free audio library, so that way this video doesn't cause any sort of copyright issues or anything. Set it up with whatever you have, and then I'm also going to configure it so that it plays through, so that the audio that I play shows up in the video instead of just going out of the audio output. All right, so stand by for that. Okay, I've got my AU audio file player set up with a file that is not going to trigger a copyright flag with YouTube. I've got it wired up to the simple EQ that we've been working on, and it's connected to the audio output. So if I push play, I'm going to hear it through the speakers, and you guys are going to hear it through this video. So check it out. All right, cool. So obviously this stuff is not going to do anything if I adjust that. All right, so that's the next thing we are going to work on. We need to set this as what opens by default when we run our application, so we will do that next. A good thing to do once you get this set up is save the setting, save the filter graph setting. I'm going to save it with my project. That's a good place to put it. Programming, put it right here, and just call it simple EQ filter graph. Okay, so now I can save that. Now I can quit this, and now I can configure the audio, configure my project to run audio plugin host when ever I run the project. So I'm going to do that with a VST3. Go here for OS X. You're going to go here. You're going to go to edits the scheme, and you're going to configure the executable. So do other. And then just search for audio plugin host. And there it is. Choose. Close. And now if we run it, it's going to run audio plugin host. And it should load our saved file. There it is. Okay. So now we can, now what we can do is actually debug our stuff. So if we add a breakpoint right here, it's going to pause execution right on that, which is cool. So now we can actually debug our code and whatnot while it's running in there. Okay, so we are done with audio plugin host for right now. Okay, we are going to connect some parameters to our filters. But before we do that, let's make a commit and just, jot down what we did. So we went through this and we initialized our chains and we got our chains up and running. Basically, you could say we added our DSP, added DSP. Right? So here's where we created our chains. Here is where we initialized our chains. Here is where we started running audio through our chains. And then this is where we did, this is where we set up our filter graph. And then here is where we added the DSP module. Okay, with that out of the way, now we can start configuring our filter chain. So go to the plugin processor.h, and we're going to go up to the top. Now let's start by extracting our parameters from the audio processor value tree state. And a data structure representing all of the parameter values will keep our code nice and readable. So let's do that first. And now next, let's write a helper function that will give us all of these parameter values in our little data struct. All right, let's go to our CPP file. Now I'm going to implement this near where I created the parameter layout so it's easy to see the names. So I'm going to put that right above this. We'll just add this here, chain settings. Okay, now there are two ways to get parameter values from the APVTS. The first way is to call getParameter and then get value like this, VTS, get parameter, some parameter name like LowCut freak, and then get value. But the problem with that approach is that we are given a normalized value. All of the functions that produce coefficients for our filter expect real world values, not normalized values. So we're not going to use this one. What we can use is a different function. We can use apvts.getRawParameterValue. Now this function returns the parameter in units that we care about. Units based on the ranges that we set up when we defined the parameters. So for instance, for the low-cut frequency, it's going to return a unit that's within this range instead of a normalized value between these two values. So let's initialize all of our data structures, all of the properties in our data structure using this function. These raw parameter values are atomic, which is handy when we are interacting with the GUI later. I'm not going to talk about any of the thread safety issues that come along with audio development in this particular course. But you can learn all about that stuff in my course, which teaches how to build the full channel equalizer, and in several talks on YouTube from the Audio Developer Conference. All right, so let's go through these and start setting up our settings. Okay, there's all the parameters. Getting them all: low cut freak, high cut freak, peak gain. Making sure we're using all the names that we used here. Let's go up to our prepare to play function. All right, we're going to do this after we've prepared our chain. Now that we have our settings, we can start producing coefficients using the static helper functions that are part of the IIR coefficients class. So we can do this auto chain. Now we can do auto peak coefficients equals make peak filter. Now we need the sample rate and our center frequency, which is going to be chain settings. Oops, chain settings dot peak freak, chain settings dot q peak quality, and then for the gain parameter, this particular parameter expects a value in gain units, not decibels, so we must convert our decibel value to gain. Thankfully, there is a handy helper function to do just that. So that's JUCE, the decibels class, and then this function. And we feed it chain settings dot peak gain in decibels. All right, let's put all that stuff on its own line so it's easy to look at. Now that we have our coefficients for the peak filter, we can set our filter's coefficients accordingly. Now you can access links in the processor chain via a get function like this, left chain.get, and it's templated. This function wants an index to a particular element in the chain via its template argument. So let's help ourselves out and define an enum that represents each link's position in the chain and use it here. All right, so we're just going to leave that the way it is. Let's go back to our header file. And we'll go down here to where our chain is, and let's define an enum here, enum chain positions. And we're going to have low cut, peak, and high cut. And this goes along with what we have here. We have a low cut, the peak band, and then the cut right here. We could change this to parametric if we wanted. Okay, now that we have that, let's go back to our CPP file, go back to prepare to play. All right, let's use it to access our peak filter link and assign some coefficients. So we're gonna go chain positions, peak, like that. All right, that's how we get that particular filter link. All right, now the coefficients object, this thing right here, is basically a reference counted wrapper around an array that is allocated on the heap. Now we want to copy its values over, so we need to dereference it. And don't ask me why the JUCE people decided to design their coefficients object this way. Allocating on the heap in an audio callback is bad, but we're going to ignore that design flaw for right now and just keep moving forward. All right, so we are going to access the coefficients, and we're going to assign it across, peak coefficients, like that. And now we just need to dereference them. Right? And then we'll do the same thing with the right chain. Okay, at this point, our peak filter has been set up and will make audible changes to the audio running through it if the gain parameter is not 0. However, any changes we make to these sliders will not cause audible changes because we are not updating the filter with new coefficients whenever the slider changes. So let's do that next in our process block. So let's go down to our process block. And we need to do this before we run audio through it. Always update your parameters before you process audio through them. Okay, so let's just copy the code we created and prepare to play, right, where we created our coefficients. We can refactor this later. Let's just copy that for now. Go to process block. Put this right after this buffer clear stuff happens. After that, put it right here. Okay, again, we can refactor this later, even though it's identical. The only thing we need to change is this guy. Let's fix this so we can just call get sample rate. All right, and now if we run it and adjust the gain, Q, and frequency sliders, we will hear some audible changes. Okay, I have run it and let's see what it gets. See what it gets us. Okay, we're just gonna mess around with the peak frequency stuff. Okay. All right, it did something. Cool. So you might notice that the filter slider is kind of wonky. That's because our ears hear frequencies. Sorry, that's because of how our ears hear versus how frequencies work. If the sound goes up 1 octave, the frequency doubles. So this is an instance of where we want to change the skew parameter of our frequency slider. Let's play around with some different values until we find something we like. So we go down to where our parameters are created. Let's see, which parameter was the skew parameter? I think it was, that's step size. Yeah, that's step size, so it's the last parameter. So I'm gonna just try 0.5 for the, let's see, I'm messing with the peak frequency, so we'll do that one first. Go like that. Let's rerun this, stop. I'm gonna change it to 0.5. Basically what it's gonna do is adjust how the filter responds when I drag the slider, okay? All right, now this is going to be more noticeable when you are messing with an actual graphical slider that you're designing versus these sliders here. So either way, I'm going to keep messing with this and we'll see what value I end up arriving on. So something you might notice here is like the range is 20 to 20,000. If the slider's in the middle, you would think that a value of 0.5 would result in 10,000 hertz, but we don't actually see that until we're way over here. And this is what I was saying before about the skew thing. So I can based on this skew that I have right here of 0.25, the from 20 hertz to 10,000 hertz is spread out across this range, and then 10,000 to 20,000 fits here in this little range right here. So that's what the skew parameter lets us deal with. Okay, so something that I'm noticing when setting that skew really far down, like 0.15 or whatever, is I hit the bottom of the range here, and it doesn't go up to the next frequency until right there. So that's a big chunk of the slider that's not usable based on this skew value of 0.15. So I'm going to put this back to 0.25, and I'm going to use that for every other frequency parameter. Okay, so with that said, we added a little bit of code, so let's go ahead and make a commit. This is going to be let's see, we connected the peak filter params to the filter. All right, let's go ahead and commit that stuff. All right, on to the next step. Okay, we are going to get the low-cut filters connected to the low-cut parameters. Now, if you remember, if we jump back over here, the cut filters were built with their own processor chain instance, and that instance has 4 filters within it. As I said before, each of these filters has a 12 dB per octave response if it is configured as a low-pass or high-pass filter. We are going to use a helper function from the JUCE framework that allows us to define IIR filters with custom orders. And we've been describing the slope in terms of decibels per octave, but the slope of cut filters is also known as its order. Okay? Also, a low cut filter is also called a high pass filter, and likewise, a high cut filter is also called a low pass filter. So let's go take a look at the helper function we're going to use. Let's jump over to plugin processor, go to the end of prepare to play, and we're just going to call it so we can jump to the definition of it. All right, just give it some default parameters. It is the design IIR high pass high order Butterworth method. Okay, so just jump to the definition of that. That's going to take us to the declaration, but we want the actual implementation of this. Okay, if we take a quick look at the implementation, for example, this little loop right here, we'll do this loop because we're going to do even numbered orders. Okay, right here, if we look at the implementation, you will see that it creates one IIR filter coefficient object for every 2 orders. So if the order is 2, we are only going to get one of these. That's what I mean, how like this gives us a 12 dB per octave cut. If it's 4, if our order is 4, we're going to get 2 sets of coefficients. If our order is 6, we will get 3, etc., etc. So what we need to do is produce the required number of coefficient objects that are needed based on what our slope parameter is set to. Now remember, this parameter had 4 choices. It was 12, 24, 36, 48. Let me jump over to plugin processor and go down to where we created our parameters. I was down here. We had 4 choices total. All right, so the first choice is at index 0. If our choice is 12 dB per octave, which is index 0, we want to get back 1 coefficient object. And to do that, that means we need to supply an order of 2. Okay, if our choice is 24, like if we're doing I equals 1, we need to supply an order of 4 in order to get 2 coefficients back. Okay, ergo, our possible orders are then, as in I'm talking about this parameter right here, this parameter, our possible orders are 2, 4, 6, and 8. Okay, so we need to add 1 to our slope choice and then multiply that by 2 to get the order to use when calling this helper function. Okay, once we have done that, we can get our array of coefficients from this helper function. Okay, I'm going to say that one more time. Our possible orders are 2, 4, 6, 8. So remember, our slope choices are 0, 1, 2, 3. So what we have to do is add 1 to our slope choice and multiply that sum by 2 in order to get the correct order to pass to this function. Okay, let's do that now. Go to plugin processor, go back up to the prepare to play function, and we're going to just get rid of this line. We're going to do auto cut coefficients equals, and now we're going to call that. All right, our frequency is going to be the chain settings low cut frequency, sample rate, and our order is going to be, remember, we're going to do our chain settings, our slope for the low cut. We're going to add 1 to it. We're going to multiply that value by 2. 2 times that. All right, let's put these all in their own line so it's easy to look at. Okay, chain settings. Remember, this is a value between 0, 1, 2, and 3. So we're going to add 1 to that. That's going to give us 1, 2, 3, 4, and then we're going to double it, which is going to give us 2, 4, 6, 8. Okay. Now we need to start. Let's start by initializing the left chain first. All right, so let's get the low cut filter chain. So we'll just do auto left low cut. We're going to get it. Chain position. Whoops. All right. Now, first we are going to bypass all of the links in the chain. All right. Remember, there are 4 positions, so we need to bypass all 4. All right. Now, it would be ideal to be able to switch based on the slope setting. So to make the code more readable, let's define another enum that represents our slope setting, since enums decay to integers, which is what our choice parameter is expressed in. Let's go to the top of our plugin processor.h. We're going to define an enum up here. So I want to have the slope amount in the enums member name, and since we can't use numbers to begin identifiers in C++, I'm going to put slope before that. So we will do enum slope, and I will do slope 12. All right, now let's adjust what the filter chain slopes are specified as. Let's change this guy right here. So instead of it being low cut slope expressed with an integer, let's express it with a slope. All right, we'll do the same thing for the high cut. Okay, now if we try to compile, we will get an error. Let's fix this error next. All right, what we have to do is change the data type right here to, we're just going to cast this to that slope type right here. Do the same thing for this line. And try building it again. Cool, problem solved. All right, now we have our enum, which gives us specific types that we can switch on. Let's go back to our prepare to play function. Oops. All right, that's down here. Now we can do a switch statement. So switch, and we want to do chain settings, low cut slope. All right. I'm too lazy to type the switch types, so I'm going to let the autocomplete do it. All right, add missing switch cases. Yes. Okay, now we just need to fill them in. If our order is 2, meaning a 12 dB per octave slope, the helper function will return an array with 1 coefficient object only. So we will assign those coefficients to the first filter in the cut filter chain and also stop bypassing that filter chain. So we will do, let's see, left low cut dot get first filter in that chain. We want the coefficients, and we're going to assign it to our cut coefficients, the first element. Now remember, we have to dereference. And then we are going to stop bypassing this particular chain. All right. Now for the next choice, we will do the same thing that we did when the slope was 12. However, the helper function will return an array with 2 coefficient objects. So we will assign to the first 2 links in the filter chain and stop bypassing them. All right, I'm just going to copy this and then copy it again and change these to 1. All right, we're going to repeat for the third and fourth option when the slope is 36 and when the slope is 48. All right, now that's obviously not, optimized. There's a lot of repetition in the code going on. We'll deal with that later. Okay, all we have to do now is repeat this for the right chain, and our slider and combo box for the low cut filter will configure the filter properly. All right, so we are going to get the right chain, and let's just copy all of this and replace all of the left low cut with right low cut. Okay. All right, as I said, there is a lot of repetition here, and it could do with some refactoring, but let's not do that just yet, okay? First, let's copy this chunk of code to our process block, just like we did with the peak filter, and we should be able to run it and test the sliders and the combo box and hear it adjusting the low-cut filter. All right, so just grab all of this, grab the cut coefficients, like that. Jump to process block. We're gonna put this after our peak coefficient stuff. Right, like that. Okay, the only difference is sample rate. We need to call get sample rate again. All right, let's run it. Okay, we should be able to adjust the low cut frequency as well as the low cut slope and hear it make a difference. All right, let's adjust the slope. So I'm going to put it around 2,500. Put it around 4,000. We can definitely hear there's more bottom end when we use a more gentle slope versus a steeper slope. All right, I'm happy with that. Okay, let's make a commit since we did some good work right there. We added the, we connected the low cut parameters to the filter. We made our enum. We adjusted our chain settings, how they are defined, and we added our coefficients, and we got them working with our working with the filter, and then we also updated how we pull them from the process block or from the APVTS. All right, cool. On to the next thing. We will refactor what we are doing. Okay, let's start the refactor with cleaning up the stuff that configures the peak filter. Let's just do a function here at the bottom. All right, we're going to update the peak filter with the chain settings. I'm going to implement this beneath where I am getting the chain settings. Now I'm going to just copy the implementation from the process block, paste it here, replace it in the process block, and then do the same thing in prepare to play. Just going to copy this stuff, paste it here. And now I'm going to call this. I'm going to do the same thing in prepare to play. Very easy. Now let's add a helper function since we will be updating lots of coefficients. Like we are updating them here, we're updating them here, 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 here. Okay, so let's go back to our header file and let's do that here. Now, I'm not sure of the exact type that the DSP IIR filter class uses for its coefficients. Take a look over here. It uses this thing, which is an alias to whatever this is. But we can make an alias to that alias very easily. And now it's very easy to declare this helper function that will update those coefficients. Now it doesn't use any member variables, so it could be a free function or it could be a static member variable, static member function. So I'm going to go with static for this particular instance because I'm already right here. I don't want to have to scroll up to make a free function. All right, and let's go implement that below where we implemented our update peak code. Okay, remember they're reference counted objects allocated on the heap, so we need to dereference them to get the underlying object. Now we can use it here. The old ones are going to be this thing. The replacements are going to be this thing. We'll do the same thing for the right chain. Okay, let's run this and then move the sliders, make sure it works. And if it's cool, then we'll delete this old code and then do the low cut filter next. Okay, so we're just going to mess with the peak filter. All right, it's making changes. Make it tight. Give it a little sweepy peak. Cool. All right, let's clean this up and then commit our changes. Let's build just to make sure that what we deleted is cool. All right, let's make a commit. All right, here we go. Commit that, stage all this stuff. Boom. Okay, we can refactor how the low cut filter gets configured next, and then we can use that same code to configure the high cut filter. Let's refactor how the low cut filter is updated. So we'll be able to use this later for the high cut filter. Now, I'm not sure what type names to use for the parameters here. So I'm going to use a templated function. So let's go to our header file and put this down here. Template type name, chain type, and then void update cut filter. Now a trick when refactoring something like this is to use the same names you were using in the unrefactored code. So I'm going to use, if we go take a look at our plugin processor, I'm going to use the same names here where I've got cut coefficients and then left low cut and then low cut slope. I'm going to use those same names for right now. Okay, so we're going to do a chain type of left low cut. I'm going to use a coefficients type of cut coefficients. And then I've got my chain settings, const chain settings. All right, so let's copy over the stuff from process block first and call it in process block and then comment out the old stuff. And we will fix any errors along the way. So let's go to our plugin processor. We're gonna grab this cut coefficient stuff and then all of this code right here. And now let's comment it out and call our function. All right, we wanna call it with our left low cut. Let me call this after this point, so I still need this thing. All right, so let's see. I still need my cut coefficients too. Update cut filter, we're gonna call it with left low cut. We're gonna call it with cut coefficients and our chain settings. Let's give that a quick build just to make sure that that works as expected. All right, we have some errors going on here. Ah, yes. Okay, so we're not passing this and we're not passing that. So comment that out and that should be good to go. All right, so we need to add some template keywords right here. Template, and that also needs to go here in front of these since these are template functions. We have to explicitly declare that they are templated like this. It's one of the more obscure C++ rules. All right. Okay, cool. Build succeeded. All right, the left cut filter is configured, so we can tackle the right cut filter with our helper function now. So we can just do this same thing. Comment out all of this code, call our helper function, and use the right low cut. All right, we'll do a quick build just to make sure. Build succeeded. All right, cool. Now we aren't using the entire chain settings object. We're only using the slope. So let's go back and change our switch statement. Okay, we're gonna get rid of this. And we're gonna change our parameter. So we're gonna get rid of this. We're gonna change this to be const slope, low cut slope. And now we can change this line to be switch low cut slope. Let's build it. We should get some errors because we need to change what we're calling it with. This is where we need to do low cut slope and then on the next one as well. All right, and if we build it, we should get no errors. Okay, cool, no errors. So let's revise prepare to play now. Let's go up here to prepare to play. And we need our coefficients, our left low cut, as well as our right low cut. So let's get rid of this code and this code. And now let's call, we'll get rid of that code too. And now we can call our code. We can call our function. All right, we'll start with the left low cut filter chain, update cut filter with the left low cut chain and our cut coefficients and our left low cut. This is where we need our chain settings dot low cut slope, and then do the same thing for the high cut or for the right low cut. Our slider and combo box for the low cut filter should configure the DSP filter properly. All right, let's test out our refactor, and if it's cool, we will delete all this code and do a commit. Okay, let's run it and see what we get. Okay, so we are going to mess with the low cut now and the slope. That's working. All right, I am very happy with that. Let's clean this up and make a commit. All right, let's clean up our header file. Okay, let's build it just to make sure. All right, looking good. Updated or refactored low cut configuration. Low cut filter configuration. All right, this is where we added our helper function. This is where we deleted our helper, our old code, and now call the updated stuff. Now, this is obviously very verbose, so let's clean this up. We're going to use a special trick. Just comment all of this out. If we reverse the switch order, we can leverage case pass-through to eliminate a ton of code duplication here. So I'm going to do that first. All right, we're just going to put the cases in the opposite order. Case slope. Okay. The way this works is like if it's the 48th, if our slope is 48, we want it to do this one. And then we also want it to do all of these. So we can just make it, instead of making it break out of the switch, we can just do, okay, if it's 48, do this, do that one here. And then also do the one that is required for 36. We can also write a templated helper function to eliminate even more duplicated code because we're doing this thing. And yeah. All right, so let's write that next right above this guy. All right, so we're going to do template. We'll add these parameters next. Void update. So we're going to need our chain. We're going to need the coefficients. And then, so we're going to need our chain type and our coefficients. And then if you notice, all of these make use of this get or set bypassed and uses a parameter here. So we are going to make this be the first parameter because if you didn't notice, when we called this function, we didn't have to provide any of these template arguments. So the compiler deduced what to put here automatically. So if we leave these as the later template arguments, the compiler can deduce them for us, and we only need to provide that index. So we're going to do that, int index. Okay. Now we can just do that update coefficients function. Update coefficients. And our old one is going to be chain dot this thing right here, template get dot coefficients. All right, and our coefficient replacement type is going to be the coefficients, cut coefficients. Is that the name I'm using there? I'm going to change that name to just coefficients. And the index that we use, if you notice, it's always when it's get 0, we always use the 0th cut coefficient index. When it's 1, we use the index 1. Okay, so whatever we put here, our index is the same thing we're going to use here. Index. All right, how convenient is that? And then we need to set the bypass state to false. So we can call that chain.template set bypassed index false. Cool. All right, now we just need to call it. All right, so remember, if we're doing the 48-degree slope, we want to call this. All right, and this is being replaced by that update function. This is where we want index 3, and our chain type is left LowCut. And our coefficient type is the cut coefficients. Let me spell that right. All right, that gets rid of these lines. All right, we do the same thing, 3, 2, 1, 0. 3, 2, 1, 0, 0. Okay. Let's test that out, make sure that works. If it does, then we can clean this up. All right, so we're going to run it. We're going to adjust this and adjust this. All right, that's filtering. Put this on 48. Put this to 5,000. All right, and we'll change the slope. And we hear more bottom end material. Not much more, but. All right, cool. Awesome. Let's make a commit of that after we clean it up. All right, cool. Is there anything in here that needs cleaning up? I don't think there is. Prepare to play. Nope. All right. Let's make a commit of that. So refactored chain update. Refactored update cut filter code. All right, cool. Got some more advanced C++ stuff going on with that. All right, now we can connect the high cut parameters to the filters. All right, so let's go over to our plugin processor.cpp and go up to the prepare to play function. First of all, now we need to let's see. Go back to my notes here. We need to rename our coefficients before we dig into high cut filter configuration. So let's change this to be LowCut coefficients. All right, now that we've done that, now we can configure the high cut chain. We're going to follow the same pattern. We're going to call the helper function to get coefficients, and then we're going to call the helper function to update the filters with those coefficients. Okay, so we're going to do auto high cut coefficients equals JUCE. Okay, we want the design low pass high order Butterworth method. All right, same thing. It's going to be the chain settings dot the high cut frequency, same sample rate, and then our order is going to be this same expression, but it's going to be the high cut slope. Okay, now we can get our left chain and right chain. Left high cut, do left chain and right chain. Okay, and now we can just call this guy. Call it with left high cut and the high cut slope, and then do it again for the right side. And then we need to use our high cut coefficients. And then we will do the same thing. We can obviously refactor this later. We can do the same thing in our process block now. Process block, let's just put this at the end of our update filter code here. And then, we need our get sample rate. And now, now that this is in place, we can run it and test it. All right, so we're going to be testing the high cut frequency and the high cut slope. All right, so I'm going to set this around 2500 hertz. Now if I change the slope, I should hear less and less high frequency. Perfect. All right, cool. Let's do a don't repeat yourself refactor, and that'll wrap it up for the DSP side of things. That was easier than probably you thought. So the first thing we are going to do is go to our plugin processor.h. Down here, let's make a function that's going to update all the filters. Now we need a pair of functions, one for the low cut and one for the high cut, and these will be called by the by this update filters function. Okay, so void. All right, takes care of those. Let's go over to our plugin processor.cpp. I'm going to jump to after the updates coefficient function, update coefficients function. I'm going to copy the relevant code from process block to the implementation for the update low cut filter. Let me grab that from process block. All right, let's just copy that. Paste that here, make sure we're getting the coefficients and then updating both chains. We're going to do the same thing for the high cut. Void simple EQ. Let's go grab that code from the process block. High cut coefficients, update cut filter. All right, now we need to implement our update filter function. So I'm going to do that below this. Now I just need to get the chain settings. Auto chain settings equals get chain settings. Now I can call update low cut filters, update peak filter, update high cut filter. Now we just need to replace all of that stuff in process block with a call to that update filters function. All right, we don't need our chain settings anymore. We don't need any of this. Update filters. Okay, let's do the same thing in prepare to play. All right, we lose all of this code, which is great. All right, let's run it just to make sure. All right, we're going to adjust all the sliders, and it should work as expected. All right, there's our LowCut. All right, LowCut's working. There's the high cut working. Let's get rid of some more high end. Okay, high cut's working. Let's mess with the peak. Cool. All right, that works. Let's clean this up. Delete that code. Go to our process block. Delete all this code. All right, let's see if there's anything else that's commented out. Nope, just those guys. Just those guys. Okay. DRY refactored DSP config. DSP filter configuration. All right, commit. Okay, cool. So that wraps it up for the DSP side of things. Okay, so that's awesome. All right, the next stuff we get to work on is the GUI side of things. We get to design a custom interface and knobs and get the response curve showing up and the FFT analysis showing up in the background as well. Okay, see you in the next one. Okay, before we start on the GUI, let's implement saving and loading of our plugin's parameter state. It's very easy to do because the plugin state is stored in the APVTS's member called state. Let me show you what that looks like. All right, so right down here, there's a public member variable. Okay, this is where all of the, basically the generic values are stored in this. Okay, so let's go back to our plugin processor.cpp, and we're gonna go to the, what's the name of this function? Get state information. The state member, as I said, it's an instance of a JUCE value tree, and those serialize to memory very easily. So we can use a memory output stream to handle the busy work needed to write the APVTS state to the memory block that this function has been given by the host. I'm talking about this memory block right here. All right, so we can just make a memory output stream. Take one that writes to a memory block, dest data. Yes, we want to append to the existing content. Let's call it MOS for memory output stream. And now we just write it, apvts.state.write to stream MOS. That's it. How simple is that? Likewise, we can do the reverse. We can restore our plugin state from memory using a value tree helper function. The only thing we need to check for is if the tree that was pulled from memory is valid before we copy it to our plugin's state. So let's use that function. All right, we want this one, read from data. We're gonna pass it data. We're gonna pass it size in bytes. Okay, once we know the tree is valid, then we can replace our plugin state and also update our filters with the saved parameter values. So apvts.replace state with the new one, and then update filters. How simple is that? So now if we run this in Audio Plugin Host, we should be able to tweak the parameters, and then they will be restored. Oh, and this, I changed the folder name, so I need to reload where this is. Okay, so for example, I'm gonna change this from 20 to whatever that number is, okay? Save it, quit. We're gonna reopen, and it's no longer 20, it is on 4573. Cool. All right, we can double click to reset it back to the default value. Our parameters are saved between loads. Cool. Okay, let's get back to using our editor instead of the generic one. So we're gonna uncomment this line, or we're gonna comment this line out and uncomment this one. All right, so now we are gonna be shown an editor that has no GUI. It just says hello world, okay? So we're back to this, all right? So we're gonna start adding knobs and sliders and all that kind of stuff. Okay, so the first thing that I want to do, we're gonna switch over to plugineditor.cpp. First thing I wanna do is give ourselves some more room. So we're gonna make this 600 by 400. All right, we're also gonna switch to the standalone plugin instead of the host for right now. Okay, if we run this, we're gonna see a bigger window. Cool, all right, definitely better. Now let's go to plugineditor.h. Now I don't want to have to type this base class initialization for every slider that I'm gonna make because they're all gonna be rotary sliders and they're not gonna have a text box. So I'm gonna create a class that does this automatically in the constructor and just use that for every slider in the GUI. So I'm gonna put that right here. We're inheriting from slider, and then we're gonna set it so that it's using the rotary horizontal vertical drag style, and then a no text box position. Now we need to add some sliders, so let's add them right here. Okay, we're gonna deal with the slope controls later. For right now, we're just gonna show the frequency and gain and quality sliders, okay? So custom rotary slider, and we want our peak freq slider. We want our peak gain slider. We want our peak quality slider. We want our low cut freq slider. We want our high cut freq slider. Now, when I have a bunch of components that are going to have the same thing done to them all the time, I like to add a function that's going to give me all of them in a vector. So that way I can just iterate through them easily. So I'm going to do that next. All right, now it's very easy to implement. Let's go to plugin editor. We'll put this after resized. All right, and all we have to do is just return a vector with all of our components in it. Now it's super easy to use. We just need to do it before we call set size. So we're going to do that right here for auto comp. Get comps, and then we can do add and make visible our component. All right, the next thing we need to do is to position them all. Now, JUCE Live Constant is a very useful tool for this. We're gonna put these right here. Yeah, when it's time to dial in specific positions, I will use JUCE Live Constant because it's basically lets me adjust positions of things while the editor is visible, which is very handy. But for right now, what I'm going to do is reserve the top third of the display for showing the frequency response of the filter chain, and then the bottom 2/3 is going to go. It's going to be dedicated to the placement of all the sliders. So I'm going to do that next. All right. So the way this works is I've got my bounding box for the component. I'm dedicating an area for the top, basically like I'm chopping off a rectangle. I'm chopping off 33% of the height. That's going to get stored in this response area. Now I'm going to put the low cut stuff on the left. So I'm chopping out 33% of the bounding box in its current form. That's going to go to the left, and then the high cut area. So if you remember, I've got basically 100%. This is taking up 33%. And so this bounds right now represents 66%. So I want to take half of that, which gives me another 33%. That's going to be the right third of the display. Now I just set my my low cut frequency slider and my high cut frequency slider to be in that left side and right side. And then for my peak slider, I'm going to set that at the top of that center column. It's going to get the top third. Same thing's going to happen here. This now, after this call, has a height of 2/3 of what it used to be. So we want half of that to give us 1/3 for the peak gain and then 1/3 for the quality. Okay, so if we run this, we're going to see knobs or sliders or whatever we want to call them. Okay, cool. So here's our big old low cut slider. Here's our high cut slider, and then here is our peak frequency. Here's our peak gain, and then here's our peak quality. And you can see these guys are they each share 33% of the of their allotted space. All right. So next, we are going to add these slope sliders. All right. Let's go back to our header file. We're going to add these over here. They're just going to be they're going to use the same custom rotary thing. So these are going to be low cut slope slider, and then high cut slope slider. And we got to add them to our list of components. And then we need to position them. So let's put them after our low cut frequency slider. We are gonna make this. Let's see. This is gonna be low cut area. We're gonna divide the low cut side of things in half, and then we'll do the same thing. Let's see. This is where we're gonna do low cut slope slider. Dot set bounds. Low cut area, and then for the high cut, we're gonna do the same thing. We're gonna do remove from top. Make sure it's that guy, and now we can do high cut slope slider dot set bounds high cut area. All right, so we're basically removing from the top of this low cut area a rectangle that is half of its original size and giving that to the low cut, and then using what that leftover piece goes to the low cut slope slider. Right. Check it out. We're going to run it. You'll see those two sliders have the same size on either side. All right. Yeah, these guys have the same size. These guys all have the same size. All right, cool. So those are the sliders. They have now been positioned on the screen. Okay, the next thing we need to do is connect them to our parameters. So let's make a commit. Added sliders to GUI. All right, commit. All right, let us connect the parameters to the sliders now. Let's go down to our plugin editor.h. Okay. Below where all of our sliders are declared, the APVTS has an attachment class which makes it very easy to connect sliders to the audio parameters. However, the name is very long, so let's use a type name alias to help out with the readability here. So using APVTS equals that super long class name, and now we can create an attachment alias as well. All right, now we just need to declare one attachment for every one of these sliders. All right, the next step is to initialize them properly. So we go up to our constructor and we have to initialize all of them here. So what we need to do is write, they take 3 parameters. So let's see, peak freak slider attachment. All right, it needs the audio processor value tree state to use. So we're gonna use the audio processor APVTS. The parameter ID, peak freak. And if we're not quite sure about that, we can go back over here and double check. So we got low cut freak, high cut freak, peak gain, peak quality, low cut slope, high cut slope. So the good thing about this project is there are not a lot of parameters, which means we can kind of get away with typing them like this. If our project had way more parameters in it, we would want to standardize how they are named and use some kind of lookup table with STD map or something. So that way it's impossible to spell them wrong here, that sort of thing. We can, just use the lookup table and some kind of enum system to index into the parameters. Okay, so let's connect this to the proper slider, peak freak slider. All right, that's 1. So we need to do this for all of these guys here. Okay, that was this one. We need to do it for all of these. Okay, once we get to this point, all we have to do is just test it and see that our sliders work as expected and their value is preserved when closing the GUI or closing and reopening the app. So let's do that right now. I'm just going to do the standalone version. Okay, we're just going to adjust this guy. I'm going to close it. I'm going to reopen it. Cool, that's at the same spot. Let's do it in audio plugin host. All right, let's run some audio through it. Okay, closing the GUI, reopening the GUI. It's where it needs to be. Gain. Save and quit that and reopen it just to double check. Reopen our GUI. Sure enough, All right, that was at 12 o'clock and now it's not. It was at 0 dB. All right, so that is working as expected. Cool. So we have successfully connected our default sliders to their parameters, and they save and load whenever we open it and close the GUI. Cool. Let's make a commit of that. Connected sliders to parameters. All right, that's where we added the attachments. Here's where we resaved something in the filter graph. Here is where we initialized all of those attachments. Our next goal is to display the response curve of the filter. So to do that, we need to give the editor its own instance of the mono chain. And to do that, we need to make all of the stuff that makes the mono chain public. So we will move all of those type aliases out of the audio processor and also make the chain positions enum public. So head on over to pluginprocessor.h. We're going to grab all of this stuff. We're going to move it to the top. Put it below your chain settings, and then grab that enum, chain positions, copy this guy, and put that here. Now we're gonna have some duplicate definitions, so let's get rid of this, and get rid of this. Let's clean it up. Head on over to plugineditor.h, and we need to give ourselves an instance of this. We can put that right here, mono chain, mono chain. All right, let's just give her a little compile test, make sure it's cool. All right, cool, build succeeded. Let's make a little commit of that. Gave editor its own mono chain, stage. Now we're gonna start drawing the response curve. All right, head on over to plugineditor.cpp. We're gonna go to the paint function. That's this guy right here. Now the first thing we're gonna do is fill it with black. So get rid of this. Actually, we're gonna use the JUCE namespace right here. Using namespace JUCE. So now we don't have to type JUCE : everywhere. Let's get rid of this. Colors black. All right, we're gonna fill it with a black background. All right, let's get rid of this stuff as well. First, we need the area that we will draw the response curve in. Auto bounds equals get local bounds. And our response area was this thing, so let's copy that. And then our width is something that we will also need. Auto w equals response area.getWidth. Next, we will need the individual chain elements. And then we will call the function getMagnitude for frequency for each filter in the chain. So let's get our chain elements. So to use that function, we are going to need the sample rate. We can get that from the audio processor. To use that getMagnitude for frequency function. So this is where we can do audio processor to get sample rate. And we are going to need a place to store all of these magnitudes, which are returned from that function as doubles. Now we are computing 1 magnitude per pixel, so let's pre-allocate the space that we need. Now we just need to iterate through each pixel and compute the magnitude at that frequency. Now magnitude is expressed as gain units, and gain units are multiplicative, unlike decibels, which are additive. So we need a starting gain of 1. Now we just need to call the magnitude function for a particular pixel mapped from pixel space to frequency space. And we will use a special helper function for that called map to log base 10. We're mapping the normalized pixel number to its frequency within the human hearing range. That looks like this. Our normalized value, let me be consistent with how I'm doing my casting. And our minimum range is 20, and our max range is 20,000. All right, now we just need to call the magnitude function with this frequency. What's it called? Get magnitude for frequency function, and multiply the results with our magnitude right here. Okay, so we just need to check if a band is bypassed, because if the band is bypassed, we are not going to do that multiplication. So if mono chain is bypassed, all right, if it's bypassed, ignore it. All right, if it's not bypassed, then we're going to do mag times equals, and here's where we do the peak band coefficients, and this is where we're going to call that get magnitude for frequency. All right, our frequency is this thing right here, And our sample rate is this thing. We just need to do the same thing for every other filter in the low and high cut chains. All right, so I'm going to do that now. And the thing to remember is that the low cut, if you remember how it's defined, it is defined as its own processor chain. So we need to get each individual element of it versus getting it from the mono chain. All right, so I've got that for the low cut. So I'm just going to do that for all 4 of the filters in the low cut, and then do the same thing for the high cut. All right, now we just need to convert this magnitude into decibels and store it. Now that we've got our magnitudes, we can convert this vector of magnitudes into a path. And we can build this path from the vector of decibels and then draw it. Okay, so let's do the first thing. Let's build our path. Now we need to map our decibel value to the response area, and a helper lambda will do the job. We could also use a free function, but I'm right here, so I'm just going to do it right here. We define some maximum and minimum positions in the window. I'm going to use JMap to map from my source input, which is a range of -24 to +24. And my output is where it's going to map to the window position. Now I came up with this -24 and +24 because the peak control can go from +24 to -24. So I want my response curve, the window for it, to have a range of +24 to -24. So that's where these figures come from. All right. So let's see, output min, output max. All right, now we can start a new subpath with the first magnitude. Start new subpath. We're going to start it at our response area dot get x. This is the left edge of the component, and the first value is going to be map mags.front. So we're going to run the first value in our magnitudes vector through this map function. And we're mapping our decibels to screen coordinates. Now we just need to create line twos for every other magnitude. All right, response curve, line 2, and we want to go to response curve, response area, get x plus I, and then we want to do map mags I. Now let's give ourselves a nice background border and then draw the path. G.draw a rounded rectangle. We're going to draw that response area. It wants a float rectangle. Corner size, let's use corner size of 4 and a line thickness of 1. Now we can, let's use a white color. All right, G.setColor. And now we can draw our path. I'm going to do a path stroke type of 2. This is going to draw a rounded rectangle with a line thickness of 1 pixel wide. This is going to draw with a line thickness of 2 pixels wide. All right, let's run this and let's see what we get. Let's open our GUI. All right, cool. We have a nice flat line inside a rounded rectangle right at the middle. Okay. Now, why aren't we seeing anything if we drag these sliders? This is because these sliders only update the filter chain in the audio processor. We also need to make them update the filter chain in the editor because it's a different chain. So let's do that next. Okay, we need to do that whenever the parameters change. All right, whoops, I'm gonna leave that open so that when this opens automatically, we get to see our GUI every time we run it. All right, so we are going to set up the filter chain in the editor to follow the parameters next. Okay, make your way to the plugin editor.h. Now, the easiest way to respond to parameter changes is to register as a listener to all of them. So let's do that. We're going to inherit from audio processor parameter listener. Now let's take a look at the documentation for this guy. Now it says here, important note, this will be called synchronously whenever a parameter changes, and many audio processors will change their parameters during their audio callback. This means that not only does your handler code need to be completely thread safe, it's got to be very fast and avoid blocking. Okay, what this means is that callbacks are going to happen on the audio thread, most likely. And this means we cannot do any GUI stuff in any of these callbacks, like update the editor's filter chain here and trigger a repaint. But what we can do is set an atomic flag that the timer can check and update based on that flag. So that's what we are going to do. So first things first, let's copy these callbacks. All right, let's go back to our editor. All right, we'll put them right here. They're no longer virtual because we are deriving from them. Let's mark these as override. All right, let's go add, let's add our timer. We're going to inherit from that so that way we can do the atomic flag thing I'm talking about. JUCE timer. Now we need to include the necessary callback. If we go to timer, we can see the callback is right here. Virtual void. All right, it's pure virtual, so we have to implement it. Let's see. All right, so in this timer callback, we are going to query an atomic flag to decide if the chain needs updating and our component needs to be repainted. So let's add that atomic flag right here below our processor. Parameters changed. It's a good name for it. Give it an initial value of false. All right, now we don't care about if parameter gestures happen, so we can just give that an empty implementation. The callback parameter that matters is this one right here. All right, now we're going to set up the callbacks. All right, below our, we're going to do this below our resized function in the editor.cpp. So first things first, let's set up that parameter value changed callback. Parameter value changed. And the only thing we want to do is set our atomic flag to true. Next, we are going to just check if it's been changed in the callback, in the timer callback. If parameters changed dot, and then here is where we want to see if it's true, and if it is, we want to set it back to false, so that way we don't want to, just like always be doing this, because if we don't make any changes to the parameter, we don't need to refresh the curve. Okay, we're going to call that guy. We want the new value if our parameters changed is true, then we want it to be set to false. Okay, now if the parameters changed, we need to update the mono chain. From the APVTS, we need to signal a repaint. And we need to signal a repaint so a new response curve is drawn. Unfortunately, all the stuff that updates the mono chain from the APVTS is private in the audio processor, so we need to do some refactoring first before we can do this and then do this. All right, so let's do that next. All right, head on over to pluginprocessor.h. Now all of these, where are those functions? Okay, yes. All right, all of these update functions need to be made into free functions. So if they use member variables, those member variables need to become function arguments. So we're going to start with the function that updates the peak filter. All right, so what we will actually do is we're going to start by turning the update coefficients function into a free function. And then that way this update peak guy can be turned into producing a peak. We can change it to produce a peak filter. Okay, so let's grab these guys. We're going to copy these. We're going to move these up to the top here. I put it below your chain position stuff. And we can get rid of that static keyword. And now we can make a function that returns coefficients. And it makes a peak filter from chain settings and a sample rate. All right, let's go over to our pluginprocessor.cpp. We're going to go to our update peak filter function. All right, and this is where we're going to implement that free function because it's just convenient to put it right there. All right, so let's do coefficients, make peak filter. And this is where we want our chain settings and our sample rate. Okay, so all we need to do is just return this call. And instead of doing get sample rate, we just need to do sample rate like that. Okay, now we need to use that helper function here. Oh, and this needs to be, we need to change this as well. We can just comment that out. All right, so we just need to call this function here. All right, let's comment this out and call it auto peak coefficients equals make peak filter, chain settings, get sample rate. And let's do a quick test to make sure that everything works as expected still. All right, we're going to make sure the peak filter works. Let me open up the high pass. I hear some sleeping. Let's do a boost. Sounds like it's working. Cool. All right, next we will get the editor to use this function. Let's clean this up. Let's do a little commit since this is kind of getting into, micro code surgery, that sort of thing. Let's get rid of that. Save this. Let's go over here. We will say refactored peak coefficient generation. All right, that's where we did that. Okay, we migrated this stuff up to there and made this make peak filter helper function. Yes. Then we implemented that stuff and started using it. Then here we implemented from parameter listener and timer and added the necessary callbacks and the atomic flag. And then here is where we displayed our response curve. Oh, I forgot to commit that stuff. So let's do that first. All right, because we want that step separated. Let's see. Here is where we drew our response curve. Let's add it. Let's do that first. Rendered response curve. That's going to be this function. That's all that is. That's all that is. We definitely want to separate that step because that was a big chunk of code that we wrote. Okay, so I was saying this is where we refactored the, let's see. Yeah, what did we do? We refactored how peak functions, how peak coefficients are generated. Refactored how peak coefficients are generated. All right, and this is where we also did that part as well. All right, and then here is where we set up for responding to parameter changes in the editor. Okay, this is where we inherited from those things. This is where we implemented the callback and the atomic flag that we will be checking. And here is where we updated that flag and then queried that flag. Cool. All right, make your way over to the editor.cpp, specifically the constructor. Yes, how can I help you? Okay. Now that we can update any peak filter link with the chain settings, we need to listen for when the parameters actually change. So let's grab all the parameters from the audio processor and add ourselves as a listener to them. All right, and now let's just loop through them. This function returns an array of pointers. Now, if we register as a listener, we need to deregister as a listener. We'll do this same chunk of code here. And do param remove listener. This. Okay, so let's go to our timer callback now that we are listening to our parameters. Okay, if the parameter changed, we need to update the monochain, so let's do that. Let's grab the chain settings, let's make new coefficients, and then let's update our monochain and then repaint. Okay, very simple. Auto chain settings. And let's make our coefficients for the peak band. All right, our chain settings and our sample rate. And now we can update our chain's coefficients. Our old ones are the monochain.get, and we want the peak. And then our replacements are going to be these peak coefficients. All right, and now we just repaint. Oh, I forgot to call coefficients. That's what we needed. There we go. All right, let's give that a test. See if we are there yet. All right, so if I adjust this, are we seeing anything? Not seeing anything. All right, soon enough. Okay, we'll get there. We can add a debug statement. Params changed, and we should see something down here if we move the sliders. And we are not. Okay. That is because we did not start our timer. Okay. So we need to go up to our constructor and start our timer. All right, let's do a 60 hertz refresh rate. I knew there was something I was forgetting. Okay, let's try this now. This should work perfectly. All right, so I'm just going to adjust the gain. All right, look at that. All right, so now we need to get the cut filters, the cut filter functions usable by the editor. So head on over to your plugin processor.h, and we need to jump down to all of these update functions. Okay, we need to make all of these public. So just grab these template functions. All right, and we're just gonna cut them and move them up here. We can put them after our make peak filter functions. Let's do a little build just to make sure that We don't have to change anything. All right, so those could have been public from the, they could have been free functions from the get-go. So now we just need to add 2 helper functions for producing the coefficients. All right, so we're going to basically do the same thing we did with this make peak filter, and we're going to be able to call them from here. So we can put them right here. If we want to implement these functions in header files that are included in 2 places, such as the plugin processor is included in pluginprocessor.cpp and plugineditor.cpp and plugineditor.h. If we want to do that, we need to use the inline keyword. Otherwise, the compiler will produce a definition for this function everywhere that this header file is included, and the linker will not know which compiled CPP file to use for the definition. So that's what we're going to write inline auto. I'm not sure what type to specify for what's being returned. Make LowCut filter. We need our chain settings again. We need our sample rate. And then we're going to use our filter design function again. I can just go copy this from the plugin processor. That's this thing right here. Let's see, I'm doing the LowCut, so I need this thing. And here's our sample rate. All right, let's just do a quick build on that. Make sure that we're not getting an error. Cool, all right, let's do the same thing with the high cut. Go back to plugin processor. I'm gonna copy the update high cut filter is going to copy this code over. Oops, this is the one we want. That goes here. This is this is just our parameter sample rate. All right, and we need a return like that. Format that properly and do a little build. Make sure we don't have an error. Okay, cool. Now we just need to update our call sites. Head on over to the update LowCut filter function, and let's change this to make LowCut. LowCut filter, chain settings, get sample rate. Same thing for the high cut. We're just going to do make high cut, get sample rate. All right, let's do a quick test before we get the editor involved. All right, this should still work. Okay, rolling off all the bottom as expected. Same for this one. Rolling off all the top end. Perfect. Let's make a commit of that refactor, because it's good to have it. Okay, this is where we connected our parameters and got the display updating. All right, here's how we updated. Let's see, this is refactored how cut filters are created. That's what happened here. Got rid of that code. Same thing happened here. And now this is where we updated. Let's see, this is where the GUI listens to param changes now. Cool. All right, we've tested our editor. Now let's update the response curve. All right, so go to your plugineditor.cpp, go to the timer callback, and we're gonna do the same coefficient update that we did here. So auto LowCut coefficients equals make LowCut filter, chain settings, sample rate. Let's cache that sample rate. No, I'm feeling a little lazy. I'm just going to copy that. This can all be refactored later, so we don't DRY, so we don't repeat ourselves. We always want to not repeat ourselves. DRY, don't repeat yourself. Okay, here we go. Auto high cut coefficients, make high cut filter, chain settings. Copy that thing right there. All right, now we can update our cut filter. Our chain is going to be the mono chain. We want the low cut. Coefficients are going to be the low cut coefficients. And our slope is going to be the chain settings slope, low cut. And then our update our cut filter, we can do the high cut, monochain.get. We want the high cut position. We want the high cut coefficients. We want the high cut slope. Okay, let's test it out. All right, so I'm going to adjust this. Okay, we are drawing outside of our response area. We are drawing though, that's cool. So the response area should be its own component, because components cannot draw outside of their bounds unless you set a flag that allows that. We will do that next, but this is a good sign that our display is responding to controls and that what we are hearing sounds like what we are seeing. Or the other said the other way, what we are seeing sounds like what we are hearing. Okay? Cool. All right, let's commit that. Response curve now shows cut filter response. Cool. Migrating this code from the editor to a separate component is relatively easy. We need to inherit from the things the editor is inheriting. And yeah, we're really not writing any new code, really. We're just refactoring what we already have. Let's go to our header file, first of all. Let's go up here. Now we need to basically inherit from all this stuff. So let's do that first. Let's do struct response curve. Let me spell it right. It's a component. And then we need to inherit from these things. Okay, we're gonna need the same, basically the same constructor, destructor pattern. And we're gonna need to migrate over all of those callbacks. Let's just copy these. All right, we're not gonna need this comment. Let's go to our CPP file. Now our callback migration, we're gonna need our parameter changed and our timer callback. So I'm just gonna copy these two guys directly. Move them up to the top, put them up here, and just change this to response curve component. Same for that. And we get a bunch of error messages. That's fine, we'll fix those in just a second. And we need to migrate over the code that registered as a listener. So let's do that here. Let's give ourselves, let's see, we need to initialize, we need to provide ourselves with that same thing. Okay, now we can initialize that guy. Audio processor. All right, now we need to migrate over the code that registered as a listener. Okay, so let's do that next. Where was that found? That was all of this stuff right here. Same for the timer. We need that too. Those guys go there. We need the destructor. We need that code. All right, so let's copy this. Okay, we're gonna need a paint function. So let's declare one of those. Void paint. We can just migrate over the entire paint function from the plugin editor. So we can literally just rename this. I'm not going to do that though. I'm going to copy it and do the proper thing. But literally, we can just literally copy this whole thing and put it down here. We'll fix all those variables in just a second. All those error messages. Number 8, we need to migrate over the parameter changed atomic value. So let's grab this from here. That should go here. We also need to migrate over our chain. Now, once we've done these things, we need to give ourselves an instance. So let's do that. I'm just going to put that here. Response curve component. And then we can also get rid of our chain. We can also get rid of our atomic. In our plugin editor.cpp, we need to go down to our function here and add it as one of our components. All right, now we need to initialize it. So let's go do that in our editor constructor. Pretty sure it's going to tell me that it needs to be initialized before the other's response curve component. Audio processor. Yes, this needs to be initialized before the attachment. For all the attachments. Finally, we need to give it some bounds. So let's go to our plugin editor resized function. And now we can actually use our response area. Cool. All right, so let's go to our plugin editor. All right, this is not going to inherit from parameter listener or timer anymore. So we don't need any of these callbacks. We don't need this atomic. We don't need the chain. So that means we can get rid of these, get rid of those functions as well. All right, so let's go to our plugin editor.cpp. We are no longer listening for those, and we're not a timer anymore. So those go away. Same for the destructor stuff. And then we're not doing any of this, so we can just continue filling it entirely with black. So we can get rid of all of this stuff. And then we don't need this callback. That disappears. All right. And I believe that's most of the errors. Let's build it and see what it tells us. That may have been it. All right. Yep. Okay. All right. So let's run and test it. All right. So this is tiny for some reason. That's way smaller than we wanted. Let's go to our resized function. Bounds removed from top. Bounds.get height. Oh, you know why? It's because our response area here in this, our response area should not be 33% of the actual component. It should just be the get local bounds. So I'm just going to do that and then get rid of this line. All right. Now if we run it, we should be good to go. Okay, cool. So let's check if we are drawing outside of our bounds anymore. And no, we are not. So that's fantastic. I told you that would be easy. Okay, let's commit that change. Created response curve component. That was a fairly aggressive amount of code surgery. Here's our response curve component with all the good stuff in it. Here's where we gutted the editor. Same for right here. All right. We've come a long way. We've done a lot of stuff. Okay, we are going to customize the slider visuals now. For this slider class, I want it to show the following. Okay, I want to see the min and max range at either end of the slider, and I want to see the parameters value in the center of the slider. I want the slider to have some customized visuals outside of those pieces of text. So I'm going to change this slider class. Let me go to my editor first. I'm going to change this slider class right here to have a custom look and feel that will do those things. So a bit of planning before we actually start. And the JUCE look and feel system works as follows. Let me jump to that. Okay, here we go. All right, look and feel methods for the slider class. Now the look and feel system works as follows. Okay, inside the component paint function, let me go to slider paint. All right, here's what happens in the look and feel system when you're painting your components. Now things are a little bit different with the slider paint, but the general practice works like this. In your components paint function, you're going to call get look and feel, and then inside of that, you're going to call one of the look and feel member functions. In the look and feel class, there are several member functions for drawing different things, and the way it's organized is kind of strange. Basically, like we're in the slider class, and the slider has look and feel methods. There's a look and feel base class which inherits from all of these things. I can pull it up in the docs, and you'll see what I'm talking about. If we go over here. Okay, so you can see that the look and feel class inherits from all of these different base classes. You know, button has look and feel methods. Text editor has their own tree view, slider, label, tooltip window. Okay, so what happens is the components, they get their look and feel instance, and then they call one of these look and feel methods. So let me go to the slider.cpp and show you what I'm talking about. In the sliders case, it uses a pimple to deal with the implementation. So I'm going to go to that so we can see what's going on. Okay, so as shown here, it's using a look and feel instance, and it is calling one of those look and feel member functions. Okay, I'll go back to this so we can see what I'm talking about. Slider look and feel methods. Okay, here we got draw linear slider, the thumb, if it's like a slider that's got multiple thumbs and stuff on it. If it's a rotary slider, a button, where to draw the text box, what kind of text box to display, that sort of thing. Okay, so it's going to call one of these member functions, and then inside this member function is where all that stuff gets painted. Okay, so for example, the vertical slider is going to call get look and feel in the paint function. If I go back here, all right, here's the get look and feel. It's going to pass it to the pimples paint function. All right, and then that's going to call draw linear slider. Okay, on that return to object. Okay, now the idea is that anything you want to draw in the actual slider part of the component is drawn with that look and feel member function. Everything that is drawn outside of it is drawn in the component's paint function. Okay, regardless of that, I don't want to get lost in those details. As I said, everything that is drawn outside of the slider area is going to be drawn in it's going to be drawn in the paint function. Everything that's part of the slider is going to be drawn in the get look and feel draw rotary slider function. Okay. Now I want the parameter value to be displayed in the center of the slider. So for this reason, I am going to display that in the look and feel member function since I consider it to be part of the slider itself. Okay, I'm going to draw the min and max parameters in the paint function and call that look and feel member function from the paint function. Okay, I know I need a bit of room for the text labels showing the range to be within this component. So that means the actual area that the slider will be drawn in needs to be smaller than the component itself. I'm also going to want to use a uniform text height for all of the text displayed here. So I'm going to need a function that's going to give me that as well. Okay, now the reason for this is because my paint function and the look and feel member function will need to call this get text height function since I'm going to be drawing text in both places and I want it to just look consistent. Okay, I also want to customize the suffix that is displayed for each parameter. So this way I will see things like 2.85 kilohertz or 12 dB per octave. All right, we will figure out what to do for the quality parameter when we get to that stage, since that doesn't have any units at all. Okay, and then finally I'm going to need a parameter so that way I can get its value. So let's go back to our plugin editor. All right, so we're gonna this class is gonna have a lot of surgery done in it, okay? First, let's rename this class. Here we're going to call this rotary slider with labels. Okay, so the next thing we need is we need to give ourselves a parameter and a suffix like I had said. So JUCE ranged audio parameter. We're going to do pointer to it. The reason I'm using this thing is because this is the base class for all of these guys. And it derives from audio processor parameter. And it contains a whole bunch of member functions that let me pull information out of this. If I go take a look at it, there's like, let's see. I'm going to need these convert to 0 to 1 and convert from 0 to 1, that sort of thing. And then there's a whole bunch of get value and all this kind of stuff. It comes from the base class. Okay, I'm getting a little sidetracked, so let's not get too lost in the minutia about that and just focus on following the code that is going to be written. All right, so there's my parameter. I'm going to give myself a suffix. All right, now I'm going to update this constructor to initialize these two member variables. All right, and now let's populate that guy. Okay, now we actually need a look and feel class, okay? We need an actual look and feel class that we can provide our draw rotary slider function in. All right. If we jump back over to this thing, this is where I can go to that slider class. Here's the look and feel methods. So we want to implement a rotary slider function. Okay, so that's what we need to provide here. So let's make a look and feel. All right, these inherit from. There's a few different versions. We're going to inherit from the most recent one, look and feel version 4. And then this is where we are going to implement draw rotary slider. So let's go to the slider class and look for that look and feel methods. And we're going to draw that rotary slider. So just copy this guy, declare it here, override it, and give ourselves a default implementation for right now. And then make this, we got to have that JUCE namespace. Cool. All right, we have our look and feel object, or our look and feel class. We need to give ourselves an instance. And then we can set that as our look and feel object. Set look and feel LNF. All right, now if we are setting a look and feel, we have to remember to unset it in our destructor. Now, as I said, we're going to need a paint function because we're going to have some custom visuals. So let's do that. Void paint. I had said we're going to need the slider bounds, which is going to be smaller than what we're actually going to. It's going to be slightly smaller than the component bounds itself. So we need some function that can provide that. JUCE rectangle. We're going to need that text height. So that's just going to be an integer. And then we're going to need to get that display string. Okay, that's what's going to show us that kilohertz or dB per octave or decibels if we're doing the gain slider. Okay, so let's do JUCE string get display string like that. Okay, now did all of these change? If we go down to our plugin editor.h, go way down here. Are all of these rotary slider with labels? Yes, they are. Okay. All right, now we need to initialize all of these guys. So go to plugin editor.cpp, go to the constructor, and all of these are declared before the response curve, so they need to be initialized before the response curve. Okay, now if you remember, this thing needs what's it called? It needs its parameter, and then it also needs the suffix that's going to get displayed at the end. So let's do the first one. So that's going to be peak freak slider. So it wants a parameter. So let's use our APVTS to get a parameter. And we already know the name. This is the peak frequency slider, so it's going to be called peak freak. And the suffix is going to be hertz, capital H. Okay, that's one slider. We got to do the rest of them. Oh, this wants a reference, not a pointer. So we dereference that. Okay, let's do the rest of these guys. And then we need our units. All right, this is decibels. Quality has no units. Frequency, also frequency. And then decibels per oct. Same thing for this one. Okay, if we build it, we should not have any errors. Oh, we have an error. What's the problem? What happened? Undefined symbol. Why did that give us an undefined symbol? Oh, we're missing a paint function. That's why. Okay, let's go to our plugin editor.h, and our paint function needs an implementation. So we'll just leave it empty for right now. All right, awesome. Build succeeded. Okay, so if we run this, we're not going to, our sliders are going to be blank because their look and feel is drawing this. Our paint function is empty. Okay, so that's why we don't see any sliders right now. But that's okay because we implemented the skeleton so we can start drawing this stuff. All right, let's make a commit of that. Implemented skeleton for custom slider visuals. All right, here's where we set up the parameters. Here's where we did all this code surgery. It doesn't look like we wrote very much, but it's a lot. You know, it's a fairly big design change. First thing we are going to do is make this just a declaration. And we will also do that with our draw rotary slider. All right, now let's go to our paint function, which we need to implement now. So let's put this at the top. Well, let's use one of these to add a space, visual delineation. So let's implement that paint function first. Void rotary slider with labels paint. We're going to use that namespace trick. Okay, we will begin by setting up the rotary slider to visually have a range of 7 o'clock to 5 o'clock. Okay, 7 o'clock. So here's 12. We're going to go 7 all the way to 5. This is probably backwards for you with the camera, but for me, I'm looking at it. If I had a clock in front of me, this would be 7 o'clock, and then this would be 5 o'clock. Okay. 7 o'clock will be where the slider draws the value of 0. 5 o'clock will be where it draws the value of 1. So let's start by setting up some angles that represent 7 o'clock and 5 o'clock. And remember that 12 o'clock is 0 degrees. And we have to use radians here, which is annoying. Auto start ang equals degrees to radians. Thankfully, that function exists. Okay, we want 180.f plus 45 degrees. All right, so this is 12. This is going to be 180, and then we're going to go halfway. So it's more like 7:30, not 7. But either way, you know, like this would be 9 o'clock. This is 6 o'clock. So 7:30 is 45 degrees away. Okay, that's the start angle. Our end angle is going to be going this way. And because we need it to be bigger than this side, we have to go one circle around, which is 2 pi, and then go 180 minus 45. Okay, so auto end ang equals this same value, but going the other way, and then added with a full rotation. Now the draw rotary slider function wants a normalized value passed to it, so we will use the slider's range for that. And then even though we haven't implemented this, let's prepare for this and just assume we'll be drawing the rotary part of the slider inside the slider bounds. So auto slider bounds equals get slider bounds. Okay, let's implement that now. All right, let's put that right here. I remember this is const. Let's just make it return local bounds for right now. We will adjust this later. So we have some basic information. We can call the look and feel function now. So get our look and feel, and now draw rotary slider. And now we just start filling this in. Okay, first thing is G for the graphic context. X is going to be our slider bounds, X position. Same for the Y. Same for the width. Same for the height. Our slider position proportional. If you don't forget that we said we needed a normalized value here, so we're going to map the slider's value. We're going to map the slider's value from the start of the range to the end of the range. And we need to map it from 0 to 1. All right, and then our start angle, we already have that, and our end angle. And then our slider is this. Okay, that's a lot. That's an annoying function to look at and fill in all the blanks if you don't know what you're looking at. All right, the important thing is this line right here. This is where we map our sliders. This is where we turn our sliders value into a normalized value. So now that we've done this, we can implement the draw rotary slider function. Let's do that up here. Void look and feel draw rotary. Come on, autocomplete. All right, let's put that all on its own lines. All right, we'll do the same using namespace JUCE trick. Here's what we are going to do in this draw rotary slider class. We are going to fill a circle, and it's going to act as the slider background. We're going to draw a border around that circle. Then we're going to convert the slider's normalized value to an angle in radians, and that's going to be between the rotary start angle and the rotary end angle. We're going to create a small vertical rectangle, and then we are going to rotate it to the angle in radians, and then draw it. Okay, so let's do the first thing. Before we do anything else, we need a bounding box. Here we've got our X, Y, width, height. Okay, so let's first create some circles that represent the rotariness of the slider. Now for these colors, I just used the app Digital Color Meter. And it lets me, just pick some random colors that I like. Maybe I like this yellow color, maybe I like this greenish color, or this color right here. That's what I use to pick my colors. So I'm just going to type in what I picked prior and use them here. So g.setColor. I don't know what that looks like right now. I just know that when I first sketched this project out, I liked that after I found it somewhere. Okay, so g.fill ellipse. And this is where we want fill the bounding box. Let's do the same thing again with a different color, and we're going to draw the ellipse, which is going to give us the border we said we were going to create. Let's take a look at that. We'll just see some circles. Cool, circles. Let's make a narrow rectangle that goes from the center of the bounding box up to the 12 o'clock position. Now, if we want to rotate something that's going to be drawn, we have to define it inside of a path. So let's create a path now. And I like using the rectangle member functions to define rectangles as opposed to using the rectangle class constructor that takes an X, Y, width, and height, because it just seems easier to visualize mentally where things are going to be. Okay, so I'm going to do that. Rectangle, float, R. The left and the right are going to be a couple of pixels off of the center, so we can do r.setLeft. So we can do center.get X, and then 2 pixels off of that, we can do r.set the right side, center.get X, 2 pixels to the right of center, and then we'll just make the top be the bounds. Top will be the top, and the bottom will be the center. Okay, so r.set top. This is going to be bounds.get Y, and then r.set bottom is going to be center.get Y. Now let's add it to our path, p.add rectangle. Now we get ready to rotate. So the first thing we want to make sure is that This thing is less than this thing, otherwise we'll get some weird explosions. So let's just add a quick JAssert for that. Rotary start angle is less than rotary end angle. This is what I was saying of how we needed to add a full cycle to it, because otherwise we would have 180 minus 45 as our start, or 180 plus 45, which is like 225 or something. And then this one would give us like 135, which is less than this. It becomes a problem when we do our JMap. So now we need to map our slider's normalized value to a radian angle. Right? So we've got auto slider ang in radians is JMap. We are mapping from our slider position proportional from a value of 0.0 to 0.1. And we're going to map it from, I'm sorry, that should be 0.f. Oh, that's 1.f. Our target range min is going to be the rotary start angle, and our end range is going to be the rotary end angle. Okay, so we are mapping our normalized slider value to be between these two rotary positions, which we defined here. We can rotate the narrow rectangle to this radian angle using an affine transform, and we have to do it around the center of our component. All right, so p.apply transform. Here's we want an affine transform. We're going to rotate it. We want the one that allows us to rotate it around a particular location. We've got our angle in radians, and our pivot point is going to be center.getX, center.getY. Now we just need to draw it. Let's build and test. Just remember, you know, we're just drawing them within their bounding box. Okay, but it is doing it, and when the value is 0, the notch is straight up and down. So that's cool. All right, so as I said, let's see, this is where it's at the 5 o'clock position. Here's where it's at the 7 o'clock position. So awesome. Okay, so they look a little wonky. Let's fix that next, but they are working. Okay, we've implemented a customized look and feel. The next thing I would like to do is add the center label showing the parameter's value next. Okay, we'll figure out that bounding issue in a minute as well. Let's make a commit of that. Added basic slider visuals. Here's where we made these implementations into declarations. And then here's where we implemented our first basic paint function, which calls the rotary slider. And then here in the rotary sliders where we actually draw the things. Okay. Let's start by drawing the slider bounds and start tweaking the get slider bounds function until it gives us a usable size. Okay, so let's go to where we're getting our slider bounds, and let's draw the slider bounds as well as our local bounds. So g.setColor red, and we'll draw our local bounds, and then we'll use a different color for the slider bounds. Now, before we start tweaking this, let's just shrink this a little bit. Okay, we're gonna want a square so our ellipses are actually circles. So let's do auto size equals, and we'll find the minimum dimension of whatever bounding box is returned to us. All right, so we've got our bounds.getWidth, bounds.getHeight. Oh, we need to get rid of this line. That's right. Okay, so auto bounds equals get local bounds. So now we know we're going to display some text on either edge of it. So let's shrink our bounding box by that size. Let's shrink our size, our square size, by that much. So we'll do size minus equals get text height. Do it times 2. All right. Now we just need to move it towards the top of our component. We need to move our slider bounds towards the top. So let's create a rectangle that has our size, but the top of it is so that it's positioned at the top of our component. So JUCE rectangle r.setSize, give it a width and height of size, so it's a square. And then we need to set, I don't know what X and Y to give it for the actual position because that's based on the upper left corner, but I can specify where the center is, and that's not going to change the size. So I'm going to do that, r.setCenter. I know I want that to be bounds.getCenterX. So that's going to put it in the center. It's going to put the center of this rectangle in the center of my component. And then I can set the Y position accordingly. r.setY 0. Or just below the top. I'm not going to do 0. I'm going to do 2. So it's 2 pixels below the top of the component. And the center of our rectangle is going to be in the center of our component. All right, now let's just return it. Let's build and test it. Boom, circles at the top, slightly below the edge, and they're in a square bounding box. Awesome. All right, let's make a commit of that, because that's helpful. All right, sliders are now circles. Oh, let's get rid of this, this line right there. Let's amend that commit. Oh wait, no, I don't want to amend it. Sliders are now circles. There we go. Okay, let's display the parameter in the center next. We will keep the circles for right now. Let's go up to our look and feel. We're going to keep these circles that are being drawn. But for now, we need the text height from our slider as well as the text itself. So we already had some stubs for these functions in place when we decided we were going to do get text height and then get display string, right? Because we wanted to be able to figure out, what do we display in the center. So in order for us to call that, we need to get a rotary slider with labels out of this parameter. So to do that, we are going to have to cast. Okay, so after we get our, after we draw our circles, we'll do a cast. All right, if we can cast it, then we know we can call those functions. All right, so this is where we can do this. Put that there. We're going to need our same path and our same rectangle stuff. All right, and then actually, since our text is going to be in the center, we need to adjust the bottom of our narrow rectangle so that it does not cover it up. So it's going to be center.getY minus, let's see. Yeah, the bottom, it's no longer going to be the center. It's going to be the center, it's no longer going to be the bottom of our bounding box. It's going to be where our center is, and then we're going to subtract the text height, which will put us back towards the top because top is 0, get height is the bottom. Okay, so we're going to the center and we're going to go up by subtracting some text height amount. Okay, so we'll just do RSWL get text height, and then maybe that much, maybe 2. We'll have to see how it looks. Okay. All right, so this is where I'm going to change this from being a regular rectangle. I'm going to add a rounded rectangle, p.add rounded rectangle, because, let's dial it up a little bit. Let's do a corner size of 2. Right now, this is where we do all of our rotation stuff. So now let's make a little rectangle that's a little bit wider than our text and a little bit taller than our text is. So that way we can have a nice, we know roughly how much text we're going to need to display. So let's make a bounding box that fits around it. And then we're going to put that right in the center of our slider. Okay, so let's first set our font accordingly. All right, we're going to just use that text height as the font. It's going to keep displaying whatever default font is currently being used. RSWL get text height. All right, this is going to use the default font at this height. All right, now let's get our text, and then let's get our string width. Auto string width equals g.get current font, get string width, text. Okay, that tells us how wide we are. All right, we can use this same rectangle. So r.set size, we're going to go str width, a little bit wider than that, and then the font height, rswl. Get text height, get text height, a little bit taller than that, okay? So now we've got our rectangle R has this bound, it's gonna basically be a little bit bigger than the bounding box for our text, okay? We need to just set the center of it to be the center of our bounds right here. R.set center, that's this guy right here. Or if we don't trust that, we can always write bounds.get center. All right, and then let's just make a black background for right now. G.set color, colors black. And then we're going to fill it in. G.fillRect R. Okay. Now let's use white text and just paint our text inside of that. So G.setColor, color is white. And then G.drawFittedText, our text inside of R. And R is a float rectangle, so we need to get it to an int to, let's see, what do we got? 2 nearest int, good enough. And then we want it centered, JUCE justification, centered, and 1 line of text. Now it's not going to build because we haven't implemented getDisplayString yet. Okay, so we need to implement that next. All right, let's put this near where we build our slider bounds. All right, so JUCE string rotary slider getDisplayString. This was const if you remember, and we will just do return JUCE string, and we're just going to return our slider's value. Let's build and test. We should see a rectangle in all black with white text in the center of every slider, showing some numeric value. Okay, cool. So we got 20,000. It's working as expected. All right, this is giving us 1, 2, 3. These are the indexes in that string array of choices we created at the very beginning. Here's our Q. All right, and here's our gain for our slider. Okay, cool. So we are not seeing suffixes, but we are seeing our values. Okay, the only thing we're not seeing is the proper slope. Okay, we should be seeing 12, 24, 36, 48. Right? We will deal with that next. All right, let's make a commit of that. All right, displaying basic param values. Cool. Okay, we are trying to represent 2 parameter types, a float param and a choice param. And the choice param has a list that we can use directly. If our parameter is a choice, then let's just use that choice param. So let's get rid of this line. And we can do if auto choice param equals dynamic cast. Let's see, JUCE audio parameter choice. If we can convert our ranged audio parameter to an audio parameter choice, then just return that choice param, get, what's it called? Get current choice name. Now for the gain and the hertz parameters, we need to amend our suffix to the parameter value. Also, I want to truncate the hertz value if the frequency is over 1000 so that it says kilohertz instead. So first we need a string object for that. Right, and then we need to specify if we're going to add the k or not. So let's assume we are not going to. Okay. Now I don't like to make guesses about what type of derived class my parameter actually is, so I'm going to use a cast here to check if it's actually an audio parameter float. Now I know I haven't added any other parameter types in this project, but just in case, I'm going to add a little JAssert in case one happens to sneak in later in the project. All right, so if it's this, I know I'm cool. Otherwise, JAssert false. If you recall the values that our parameter ranges had, you know that the hertz parameter is the only one that can possibly get over 1000. So that means we can just check if our value is over that and then divide by 1000 to get a kilohertz value. Once we have that, then we can say, yes, please add a k to the suffix, and we can convey that with that Boolean flag we used earlier. So if value, first we need to get our value, float val equals get value. If our value is greater than, if our value is is 1000 or higher, then this is when we want to display it as kilohertz. So we will say val divided by equals divided by 1000. So if it's if the value is 1000 hertz, we're going to see 1 kHz like this. Add true. Okay, now the string class in JUCE has a constructor which lets you convert a floating point number into a string, and one of the parameters is how many decimal places to use. Now, if I'm displaying a value as kilohertz, I only want to see 2 decimal places. We already know that dividing 1001 divided by 1000 is going to give us, let's see, 1000 1001 divided by 1000 will give us 1.001. I don't want to see that. Okay, I just want to see 2 decimal places. So according to this constructor, let me pull that up real quick. This one right here, float value, okay? It says number of decimal places. If this number is greater than 0, the number will be formatted using that many decimal places, adding trailing zeros if required. If the number is 0 or less, the number will be formatted using the C++ standard library default format, which uses scientific notation for large and small numbers. According to the documentation, if you go back over here, according to the documentation for this constructor, if a 0 is provided for the number of decimal places, the number will be formatted using the STL with however many decimal places are needed. So this will work out when we are displaying decibels or quality versus the hertz. Okay, so we're going to do str equals juice string. Where is that one? It's down here somewhere. This one, float. Okay, our float val for our number of decimal places. If we are adding the k, we want to see 2 decimal places. Otherwise, the STL formatting will be just fine. So add k. If we're adding the k, give me 2 decimal places. Otherwise, give me however many are actually needed to display the parameters value. All right, now the final thing is that we had said that the quality property does not have any units, which means we did not supply a suffix. If we go back down here, you'll see what I'm talking about. Okay, hertz and decibels have a suffix, but quality does not have a suffix. So if the suffix is not empty, let's add a space after the number and then add the suffix. If suffix is not empty, we can do str, add the space. And then if we are doing a hertz value, which is over 1 kilohertz, let's add the k. If add k, str, add that little k like that. Now we just add the suffix. And then we're done. Return the string. Okay, let's run that and check it out. Boom, 121 hertz, and let's raise that to be over 1,000. There we go, 1.01. Awesome. Okay, and then these guys, cool. All right, I'm not too mad about when it's showing a negative and how it's not showing the it's not showing it. The rectangle is changing size. It's, you know, that's just like a minor detail that we don't need to fix. And now this is displaying the correct slope values. So that's cool. All right, let's ditch those bounding boxes that were showing the rectangles. It's these guys right here. I'm going to leave them in as comments though, because, you know, if we ever need to debug this some more, it's good to just, you know, it makes it easy to uncomment them and display them later. Let's take a look one more time and see what we've got. All right, that's nice and clean. Cool. Let's make a commit of that. All right, so implemented displaying the parameter value with suffix. Cool. Let's add the labels next that will show the minimum and maximum values that our parameters can have. I would like the minimum value to be drawn right outside of that 7 o'clock position on the slider, and the maximum value to be drawn outside of the 5 o'clock position. Here is how I have decided to go about implementing this. Okay, we're going to have a simple data structure which will hold a normalized value and the string that should be positioned at that normalized position. Okay, so we'll put that, let's see, let me go to a plugin editor.h. All right, we're going to put that right here. Okay, so we'll do struct label position, give it that normalized value, and then the string that's going to get displayed. All right, now that we have this structure, we can just give ourselves an array of them. And then all we have to do is add some values to that array and then draw them in our paint function. All right, let's make our way over to the paint function. Okay, we're going to draw this after we draw our slider. So let's see, what we need to do is create a bounding box that can encompass our text and then put the center of that bounding box at whatever normalized position we have decided on around our slider's circumference. Once we have that bounding box, we can just use the graphics function draw fitted text like we did right here. We can do the same thing. We can do that to draw our label inside the bounding box. So first things first, let's get the center and radius of our slider bounds. Auto center equals slider bounds dot to float dot get center. Okay, we want this in floating point numbers. And then let's get the radius from that. Auto radius equals slider bounds dot get width. And then give me half of that. Okay, now let's set up the text color and size of the text. I'm going to use the same text color. No, I'm going to use a different text color. I'm going to use like a greenish looking thing. Again, I figured this out using that digital color meter app. This thing right here. I found a nice green that I liked and just jotted down the RGB values. Let's do that next. G.setColor. I've got a value of 0, unsigned int. Value of 172 right here for that, and then 1 for the blue. And then we need to set our font. Okay, we're going to use the default font with this text height. We need to iterate through our labels. So auto num choices equals labels.size. And here we go. For int I equals 0. I is less than num choices plus I. All right, now let's convert that normalized position into a radian angle. So auto position equals labels. Okay, and we want to make sure that it's between 0 and 1 just in case. All right, now let's JMap it like we JMapped this thing right here. Actually, we can just grab this. Auto angle equals this thing. And this is going to be our position. And our start ang is going to be what we set up here. Same for the rotary end. Okay. Now we can use one of the point class member functions, particularly this one, point. I'll show you the member function. Get point on circumference. We can use this member function to find the center point we will use for this bounding box with this particular radian angle. We have our center that we will use. So center.get point on circumference. Our radius is going to be radius plus get text height. Yeah, we want it to be a little bit further out from our rectangle. So we'll do like half the text height, maybe a little bit of another cushion, and then our angle is going to be like that. So if you're wondering where this number came from, let me turn this back on and draw this. Okay, so I'm talking about, here's our center of that bounding box. We're gonna go, if I go radius away from this at this angle, I'm gonna end up like right at this point right here. So that's why I'm adding text height to it, because text height is this amount. So I wanna go that much more away. That's gonna kind of put me near this corner, right? It's gonna be different, you know, it's gonna be like this vertical distance away from this angle. That's why that's gonna do that. That's what this line of code does. It's going to get me that point. Auto C equals that. Okay, we have our center point. Now we can get the width of our string from the currently used font like we did up here. I'm going to do that same thing right here. And then we're going to make a rectangle that's going to use that width as well as our text height to define its bounds. So let's do rectangle float R. We need our label. Do we need that yet? Yes, we need our label because we need to do r.setSize. So auto str equals labels label. Okay, and then we can do r.setSize. Now we will use the size using that getStringWidth helper function like we showed before. This is going to be g.getCurrentFont, getStringWidth, str, and then our height is going to be getTextHeight. Now we can just set our center, r.setCenter, and then maybe shift it down a little bit just in case so it doesn't collide. r.setY. Okay, we'll get the current y as it is, r.getY. And we'll just add a little bit, just shift it down just a little bit more. Okay, and then now we can just draw our fitted text, and hopefully this will be in the right position. Okay, so g.draw fitted text. Our text is going to be our string. Area is going to be r. R is a float rectangle type, so we want to get the nearest int. We need to convert it to integers. We'll do the same centered and one line. Try to fit all the text on one line. Okay, so just to recap, we are drawing we've got the center of our rectangle right here. We're gonna go at some angle away from it like this. And then this would put us right on the edge of the circle, and we don't want our rectangle to be centered on the edge of that circle. We want it to be a little bit further out and then down a little bit. So that way it doesn't collide with the circle. Okay, so this gets it right on the circle. This gets it a little bit past the circle, and then this shifts it down from the circle. All right, let's check that out. Okay, why is this not displaying anything? Oh, because we didn't initialize it. Duh, we need to actually provide some labels first. So let's do that next. 36, step number 36. So we need to go to step number 37. Let's go to our constructor in our, where is this? This is in our plugin editor. Okay, so we will do this before we make our components visible. Let's add our min and max ranges. So we'll start with the peak freak slider. Okay, and this is where we'll go to our labels, and we'll just add one of these label positions. So at position 0, I want to display 20 hertz. And then at position 1.0, we will display 20 kilohertz. And then we'll do KHZ like that. Let's see if that looks like anything. Okay, cool. 20 hertz, 20 kilohertz. Nice. All right, let's make a commit of that. Ram min max values. Stage. All right, let's do the rest of them. We got 20, let's see, negative 24 dB and plus 24. Okay, cool. So my gain slider, whoops, I always spell that wrong. Okay, so my gain slider is going to show negative 24 and plus 24. My quality will show 0.1 and 10.0. And then low cut and high cut are going to show 20 hertz and 20 kilohertz. And then the slope sliders are going to show 12 and 48. And I don't see a need to make it display the decibels per octave thing. Anyway, let's run it and check it out. Okay, let's get rid of these bounding boxes. Where was that? That's up here somewhere. That's right here. They're handy to have, handy to be able to just pop them in there to help debug your visuals. Okay, cool. That's looking pretty clean. I'm happy with that. All right, let's adjust these positions a little bit. I'm going to make the display a little bit taller. And then, and I'm going to do that because, let me put that back. Okay, it's a little bit cramped for me here. So I'm going to make this just a little bit taller. And then we're going to use JUCE live constant here. I want to change the height of the response area. Okay, so we'll get a little look at how that's done. So we'll do float h ratio, height ratio. I'm going to use JUCE live constant here. We're currently using 33. Okay, so now we can do this here. And we're going to dial in our height ratio to figure out what size the response area should be. Okay, cool. So now we are looking at, what am I adjusting? All right. Okay, I'm doing that because when this goes like that, it covers up that. So if I shrink this a little bit, does that go away? All right, that seems okay. I need the slider text to not overlap, but it's doing it anyway, so perhaps I need to shrink this length so it's a little bit smaller. Or maybe it's not a thing. Either way, 25% looks good. The knobs are a little bit bigger. I mean, if we wanted to, we could just make this like really big, but that just looks kind of weird, and we don't even see our slider thumb now. So that's the big problem, is I want to see more of the slider thumb than I'm currently seeing right now, which is why I'm making, if that's like that, I want to make this a little bit, I want to see more of the thumb. Okay, so I think 25 looks okay. It's pretty easy to see where the thumb is. Okay, so we'll stick with that. We'll do 25 for that value. Okay, so we'll change this to 25.f divided by 100.f, and we'll just comment that out because it's always, it's always useful to be able to uncomment that and use it to dial in those other positions. Okay, now I think if we take a look at that, there's one other graphic change I want to make. Now, I don't like this gap right here, so I want to put a little bit of room between where the sliders are and where this response curve component ends. So we can do that by just removing a little bit from this bounds before we do all of this stuff. That's pretty easy. Bounds.remove from top. I'm going to just remove 5 pixels. Let's see what that looks like. Okay, that's clean. I'm happy with that. Okay, so let's open this up. Now let's see what this does. I'm just going to customize this a little bit. Save it. Close this. Okay, so these parameters are not drawn on here right away. Okay, so that's a bug that we need to fix. So let's open this back up. Let's quit this. Let's see if we can solve that. Okay, so this is caused. Let's go look at our timer callback code. Response curve component. Okay, the chain is only updated whenever the timer callback determines that this parameter is true, and this parameter is only set to true whenever the parameter value is to change. So if our GUI is displayed, have the parameters changed from since they were initially loaded? No, they have not. Okay, so there's a couple ways we can do this. First of all, the hacky way to do this would be to say, you know what, this parameter has changed the first time the GUI loads, but that's kind of hacky. Okay, what we need to do is just refactor how that stuff gets set in the first place. So let's make an update chain function, and now we can just call this in our timer callback and from our constructor. All right, so this is going to update the chain during construction, which means the chain will give us the proper magnitude values when we've painted for the very first time. So let's do that. Let's add let's put that right here. Okay, we're just going to move that code out of timer callback. Void response curve component, update chain. We can just grab all this stuff. We're not going to repaint though. Okay, now we're just going to call it update chain. And then we can call it in our constructor as well. Let's call it before we do our timer. All right, let's run it. And we should see the chain get updated automatically whenever we close and reopen the GUI. Okay, so that's showing up as correct. I'm going to change this param to that. Okay, that's on 9dB. So notice there's a bump right there. I'm going to close this GUI, reopen it, and that bump is there. Cool. Bug solved. All right. Let's make a commit of that. What do we have going on here? Fixed response curve bug when first opening the GUI. Okay, cool. So we have our, this is where we started displaying the star values, and then this is where we actually added those labels. Here's where we dialed in the final position for all the components, and then here's where we fixed the response curve issue by refactoring what happens in timer callback into its own function that we can call from our constructor. Okay, cool. That wraps up the response curve and customizing the knob visuals. Okay, the next thing to do is to put a grid behind the response curve. And then after we do that, we can add the spectrum analyzer. And then after we do that, we can add the bypass buttons. Okay, so we got 3 big things to do before we are done with this component, but we are almost done with this project. So awesome. It's progressing very quickly at a pretty good clip. Okay, let's give this response curve a proper background component that's going to show the frequency plot. And since we don't need to recreate this every time the curve is updated, we are going to pre-render it into an image. So let's head over to our plugin editor.h, and we will do that right here. Now, we need a place to make this background image, and the resized function is a good place to do this because it is called whenever the component bounds change, and it is called before the first time that paint is called. So let's declare that guy here. All right, let's go to our CPP file. Let's put this after our paint function. The first thing we will do in this resized function is make a new background image based on the width and height of our component. Okay, so first let's declare this void response curve component resized. So, okay, we're gonna create a new background image. Then we will create a graphics context, which will draw into this background image. And then from there, we can just do the usual paint stuff, except we are drawing into this background image directly using the graphics context that we created. So let's start, we'll start with that. Okay, we're gonna use an RGB context, an RGB pixel format, the width and the height for the dimensions, and then we want to clear the background. All right, now we just need the graphics context. Now I want to draw frequency lines. So I'm going to create an array that I can loop through and convert these frequencies to window space and then draw them as vertical lines. And these values that I'm using for the frequencies are the standard values people use when producing these types of plots. I mean, you can come up with whatever you want, but these are the pretty standard values that people use, and they're in multiples of 10. Or they scale up by a factor of 10 each time. So let's do, so I'm gonna do 20, 30, 40, 50, 100. I'm gonna multiply that by 10. And then the last one, since that's the top of the human hearing range. All right, now I'm going to set my color to white. I'm gonna loop through the frequencies. I'm gonna map them from this frequency linear space to a normalized position, and then I'm going to draw a vertical line. All right, let's take a look at that. I'm sorry, actually, before we even do that, we need to display it in Paint. But before I do that, I want to show some gain lines as well. So I'm going to do the same thing. I'm going to create an array. I'm going to loop through it, and I'm going to convert each value in the array to a window position and then draw it as a horizontal line. So let's create that next. I'm going to do lines every 12 decibels. Okay, so remember I'm using 24 and negative 24 as my range because that's what our slider can, our gain slider can, those are the ranges of that gain slider. And then it's important to remember that the bottom of the window, we want this negative 24 to be mapped to the bottom of our component. And then we want the positive 24 to be mapped to the top of our component. And then we're just drawing a horizontal line from the left side to the right side. All right, now we just need to go to our paint function and draw it in the background. G.drawImage, image to draw as background. And it wants a float rectangle, so get local bounds to float. All right, let's take a look. All right, cool. It looks like something. Good times. So for this graphic stuff, we're gonna switch to the standalone plugin. So that way we don't need to deal with audio plugin host at the moment. We're just looking at graphics changes. So let's look at that one more time. Okay, so the first problem is that there's a lot of collision happening, like our plus 24 line and our negative 24 line. We don't even see them. So we need to shrink the bounding box that we are using to compute these values within, which means we also need to adjust how our path is going to get produced. So let's go to our editor, editor.h, and then below this, let's add a function that will give us the area we will draw our background grid in and also our response curve in. I'm going to call mine getRenderArea. It's going to return a JUCE rectangle. Now go to our plugin editor.cpp, and let's go to the bottom of that after the resized function. All right, so let's use some JUCE live constant to figure out the bounding box of this. All we know is that we are going to reduce our local bounding box, but not by how much, so this will be a good chance to figure that out. So we're going to use the reduce function. We're going to reduce it by some amount. We'll do, start with 5. I'm going to reduce both the X and the Y. And it's important to make sure you put JUCE live constant on its own line. one instance per line. Okay, for right now, we're going to stop drawing the vertical lines as well as the horizontal lines. And we're just going to draw the render area. Okay, so let's run this and let's dial in the values here. Let's move this out of the way. Okay, so if we increase this, we shrink it, we shrink the width. And then if we do this one, we shrink the height. Okay, so let's figure out what looks good. I know I'm going to want to have some text on this side and on this side showing like the actual values for the lines, like 0 dB, plus 24 and minus 24, and then whatever I'm going to come up with here. And then we need our frequencies to get displayed either above or below somewhere. So let's dial this in. All right, and I like shrinking it by 10. I think this is a good width, and then height-wise, I don't think I need that much. I'm going to go with 8. So 10 for the width reduction, and then 8 for the height reduction. 10 and 8. So let me just make that change here. 10, 8. Put this on its own line for right now. Okay, I'm happy with that. So let's make the response curve sit within this rectangle now. All right, let's go to our paint function. Now all we have to do is change this line right here. Response area is going to be get render area. Auto response area equals get render area. Talk about easy. I am glad we planned ahead on that by using this response area to represent what we are drawing. Let's take a look. Okay, cool. So this is being drawn inside here. It's also, we're getting a little bit of the path being drawn outside of it because our response area is smaller than our component, and this path is being drawn inside, the entire component. So we'll figure that out in a little bit, but this is cool. All right, we're making progress. Now I'm going to change this from being reduced on all sides to being reduced mainly on the top and the sides. We want to leave room for the frequency label on the top and the dB levels on the sides. But for the bottom, I don't really care about that. So we're going to get rid of that. We're going to do bounds.remove from top. We're going to give us a gap of 12 at the top. From the bottom, we're just going to do a little gap. Maybe something like that. And then on the sides, I think we need more than 10, so we'll do 20. Bounds.remove from left, 20, and then bounds.remove from right, 20. All right, let's take a look at that. Okay, cool. So we've got 2 pixels of space here. We got our 20 here. This is plenty of room to have small text, and then same for on the top. We can put some low height. Yeah, like use a font that's not very tall for right there. Okay, so let's go, let's separate the render area from the actual analysis area. So let's add another function here. And it's going to be called getAnalysisArea, and that's actually going to be what we draw the response curve within. So if I pull this back up, when we see you'll have to just imagine the grid lines for right now. But just imagine that like, we're not going to have the plus 24 be underneath this, like right at this orange line. It's going to be slightly less than it. And same for the bottom. Our negative 24 is not going to be on this orange line. It's going to be slightly above it. So that's what I mean when I say our analysis area is going to be a little bit smaller than our render area. All right, so let's implement this back to our CPP file. Put this right here. All right, we're going to start with our render area. And then we're going to trim some off the top and trim off the bottom. So that way we can see the top and bottom line of our grid as I had explained a moment ago. Bounds.remove from top. Gap of 4 should be nice. Bounds.remove from bottom. Same size gap. All right, now let's use this instead of the response area in our paint function. So response area. Not get local bounds, or not get render area. Let's use get analysis area. All right, so let's take a look at that. Okay, all right, so we're seeing our orange rectangle in the wrong spot. So let's take care of that. That goes down here. That's at the bottom. That's this guy right here. So instead of using the response area, we want to use the render area. Okay, cool. All right, so now let's go back to our resized function, and let's draw our analysis area. All right, yes, let's display our analysis area so we have an idea of where this actually is. All right, cool. So yes, it's slightly set inside our orange render area. Okay. So let's see. Let's go up to our frequencies. We want to be drawing inside of this analysis area instead of the local bound. So let's cache some information about this analysis area. Let's do this right here. We'll go to auto render area equals get analysis area. And now let's cache the left, right, top, bottom, and width. Okay, because we need the left and the right for our horizontal lines. We need the top and the bottom for our vertical lines. And then we also need the width for, is it this thing? Well, either way. All right, let's just start caching them. Auto left equals. Since the frequency labels as well as the vertical lines will need this X position, let's just cache this value into an array. All right, so we're going to use the same mapping code where we convert our frequency value to a normalized position, and then just compute that to a window X position based off of this left edge of our render area. All right, now we can actually draw our vertical lines. Let's get rid of this. And I'm going to use, I'm not going to use white, I'm going to use dim gray for this. So instead of looping through our frequencies, let's loop through our X positions. We don't need this line anymore. Instead, we need this right here. We're going to draw X, and from the top to the bottom. All right, now let's go to our gain, and let's see, we can make it, instead of using our get height and 0, we can use our bottom and top. Okay, and then I want to make the 0 dB line have the same color as our min and max slider labels, and everything else is going to be gray. So that way we'll be able to visually see where is 0. So we will do g.setColor. If it's 0, then we're going to use that one color. Otherwise, we're going to use a darker color. We could, a dark gray is cool. All right, let's go find that green color. That's in our slider. Where is that? Where do slider paint? This color right here. And this should probably be standardized into a static color at some point. Define it at the top of the header file. But for right now, this is good enough. All right, so we're going to use that right there. All right, and we don't need this border anymore, so let's run it and take a look. Oh, I forgot to draw the line. So g.draw horizontal line at y, and then left, right. So we should see a green line in the center. And there we go. Awesome. It's looking good. Okay, so the next thing to do is to draw the frequency labels. Let's make a little commit of what we've done so far. All right, we basically roughed out the grid lines. Added grid lines. Added grid lines into. So let's see. We actually we added grid lines. We also pre-rendered grid into background image. Cool. Okay, so frequency labels. Let's draw these down here. Get rid of that line. We'll do a cleanup at the end. Okay, so I want to draw these with that light gray color, so that way they pop out a little bit. So let's set our color there. I want to use a font height of 10. If you remember our render area, we gave ourselves a room of 12 between the top of our component and where our render area is. So I'm going to draw inside that little 12 gap. So that's why I'm going to use a font height of 10. And if I need to tweak that, I can tweak it later. All right, so now what we will do is loop through our frequencies and X's and draw the text above the grid at those particular positions. Now I'm going to use the same trick that I used when drawing the labels for the min and the max range, where I added kilohertz. Use that same trick right here. All right, and then we can just assemble our string, lowercase. All right, and we're going to do the same trick that we used with the string width and building a rectangle around it. Very simple stuff. We've got a rectangle. We're going to give it a particular size. I know where I want the center X, but not the Y. And that's okay because I can set the Y after I have already set the X position. All right, all we need to do now is just draw our text. All right, let's run it and take a look. All right, cool. We got some collision of text going on here. That's okay though. We'll figure that out next. All right, so it looks like the 40 and the 30 and the 40 are getting pretty close. 300 and 400 collide a lot. 3K and 4K collide a lot. So let's get rid of those. All right, and let's try that again. Much cleaner. These are much easier to see now that they're not colliding on each other. Cool. All right, so let's add a commit for that. Added frequency labels. And we also thinned out number of frequencies. All right, let's do the gain labels next. All right, let's go to where we are looping through our gain labels. Is that right here? So we're actually going to do this down here. All right, we're going to loop through our gain labels the exact same way. We're going to need that Y value. All right, now we need to make a string with the gain value. If it's greater than 0, I want to see a plus sign. If it's not, it's going to be a negative number. So let's do the same thing. String str if gdb is greater than 0. Add the plus sign. And then just feed in that gain value. All right, let's get the width like we did before. And then we're going to build a bounding box around that, just like we did before. Same thing here. Okay, now we're going to draw these on the right side of the screen. So our X position is going to be the width, get width, minus our text width. And then our height is going to be, let's see, I'm not sure where I want the Y position to be, but I do know that I want the center of this rectangle to be lined up with this. So I'm going to use the r.setCenter. Use this thing. I know I wanted to use the current center X, and I know I want this to be Y. Okay. So like I said, I know where I want the left edge of this to be. I don't know where I want the Y position to be, but I do know that I want the center of this text to be at this Y position, which is the same position we are drawing our gain lines. So I can do that same trick where I've got, I know the X, the rectangle has the current X position, so I can get the center X of the rectangle, and then I can set the Y, I can set the center with this Y value. Okay, now let's just set our color. I want to do the same trick I used here where I set it to green if the line should be green. The only difference is I'm going to I'm going to draw the text as light gray to match the other color I used for this text. All right, so this is going to give me a greenish text color for the 0 dB mark. And then now we just need to draw our text. That's this thing right here. All right, let's take a look at that. All right, cool. We got plus 24, plus 12, 0 in green, minus 24, minus 12. Awesome. All right, let's make a little note about that. Added gain labels to grid. Okay, let's add another scale. Let me pull this up on this side. Since we are going to be doing an analyzer, let's add another scale on this side for that. Okay, now our gain range for the peak band was 48. We could do from plus 24 to minus 24. So let's do the same for the analyzer. We'll do 0 to negative 48. So this is easy. All we have to do is subtract 24 from the decibel value. Just do that right here. We can go str.clear, clear out our string. Let's fill it in again this way. Since we're not going to have any values over 0, we don't need to worry about that. So we can just do gdb minus 24. All right, now let's just adjust the text bounding box like we did before. So we know our X position is going to be on the far left, not on the actual left, but like 1 pixel off from it. So r.set x 1. We need to recompute our string width. Then we need to set our size accordingly. Then we can set our color to just always be light gray. That was written up here. Then let's just draw our fitted text inside this rectangle. All right, so that's good times. All we are changing is the X position and then the actual size of it. All right, let's take a look. All right, cool. We got our 0, minus 12, minus 24, minus 36, minus 48. Cool. All right, so that takes care of that background grid. Let's do a little cleanup. And then, yeah, do that cleanup. Let's take a quick look through all this stuff. Here we go. Get rid of that line. Get rid of this. Okay, that takes care of those guys. So what we're going to do next is the FFT analyzer and then the bypass buttons. Okay, let's commit that, what we added here. This was a code cleanup. And then we also added analyzer decibel marks. Added analyzer decibel marks, cleaned up code. Awesome. All right, let's head on over to pluginprocessor.h. Okay, go up to the top. Now, our analyzer will display 2 FFT curves, 1 for each audio channel. That's because the FFT algorithm operates on a single channel of audio. Okay, we are going to express that programmatically. All right, this is effectively 0, effectively 1. Okay, now the FFT algorithm operates on a fixed number of samples. The host is passing in buffers which can have a variety of different sizes. So we need a way to collect them into blocks of fixed sizes. That's what this class does. That's what this class right here does. I'll zoom out a little bit. I'm not going to explain how it works. All right, if you want to know how this class works or how to make it, you can check it out in my PFM Project 11 course where I explain how to make every little part of this and how to get it all to work together. Okay, let me zoom back in. Next, while our single sample FIFO is collecting individual samples from the buffers into blocks, we need a FIFO that the GUI thread can use to retrieve these blocks that this single channel sample FIFO has produced. That's what this class does. That's what this class right here does. All right, if you want to know how to make this or how to write it, you can learn how this gets put together in my course PFM C++ for musicians. All right, you can check those guys out. Links in the description and all that good stuff, okay? Let's go to the next part. All right, we need some instances of these things. So let's go to our class down here. Now we're going to need one instance of this single channel FIFO per audio channel. Remember, we are working on stereo buffers. Because it is a templated class, I'm going to create a type alias to the type that we will be passing into it so we don't have to type so much. Okay, these also need to be public because the GUI is going to need to access them. Okay, we are going to need pointers to this class in the GUI side of things, and this alias will make it easier to declare instances, to declare pointer instances of that single channel sample FIFO. So let's do that now. And then let's declare our instances. All right, the single channel FIFOs need to be prepared, so let's go do that in our plugin processor, prepare to play. A lot of Pete words right there. Prepare to play, go to the bottom of it after our filters. This is where we're going to prepare our FIFOs. Left channel FIFO.prepare, samples per block. Same thing for the right side. Okay. Now we just need to push buffers into it. So go to the process block, and at the very end, after our processing is done, we're going to update it with our buffer. Same for the right side. Okay, let's go to our plugin editor.h, and we are going to go to our response curve component at the bottom of it. We are going to convert some audio samples into FFT data. This is not going to be simple. Okay, we're basically going to build this system. Let's see, I have this kind of drawn out on this grid. Let me make it bigger because it's important to know what's going on. Okay, we are basically going to build this system right here. So here's what happens. The audio buffers from the host go into the single channel sample FIFO right here. Okay, the single channel sample FIFO spits out fixed size blocks. Okay, then these fixed size blocks go into an FFT data generator. All right, and this thing spits out FFT data blocks. The FFT data blocks go into a path producer right here, and then the path producer spits out JUCE path instances. And finally, the GUI consumes those and renders the paths. Okay, so buffers of random size are fed into the single channel sample FIFO right here. This thing spits out fixed size blocks. Then those go into an FFT data generator. The FFT data generator spits out FFT data blocks. Then those get run through a path producer, which produces JUCE paths, and those get rendered and consumed by the GUI. Okay, that's what we are going to build. Okay, so let's give ourselves a pointer to one of the audio processor's single channel sample FIFOs. Single channel sample FIFO. It's that block type, simple EQ audio processor block type. This is and we're doing a pointer to it. Left channel FIFO. We're just gonna do the left side for right now. All right, let's go to our CPP file. Let's go to our response curve constructor. And we need to initialize this guy. Let's put this on its own line. This is where we're going to do left channel FIFO, and we want to pass it the audio processor dot, what's the name of that thing? The left channel FIFO. Okay. Let's go to our timer callback. Now this is where we are going to coordinate all of those pieces of the system. Let me pull this back up. We are going to coordinate this thing with this, and with this. Okay, we're going to coordinate all those little parts together. First thing we're going to do is the single channel sample FIFO. So here's the logic we are going to use. While there are buffers to pull, if we can pull a buffer, we're going to send it to the FFT data generator. So the first thing we need is a temp buffer to pull into. Okay, we're going to do this before all of this parameters change stuff. Okay, let's make our temporary buffer. All right, just before we do that, actually, let me go through and just clarify the interface for our FIFO guy. Single channel sample FIFO. All we need to care about is like, how do we feed it buffers? How do we prepare it? And then how do we get buffers from it? Okay. This is how we know how many we have, and this is how we actually get a buffer from it. Okay. Very simple to use. Same thing for this FIFO right here. We just push stuff into it and pull stuff out of it and make sure that we've prepared it with however much pre-allocated space we need. Okay. All right. So we need to go through this logic again. You know, while there are buffers to pull from the single channel sample FIFO, if we can pull it, then we're going to send it to the FFT data generator. All right, so let's add our while loop. While left channel FIFO, get num buffers available. If that's greater than 0, if there are more than 0 buffers available to be pulled, let's try to pull one. Give me that audio buffer, temp incoming buffer. If we can pull one of these, then we are going to send it to the FFT data generator. All right, now it is very important that we maintain the order of the blocks coming in from the audio thread. So before we send audio samples to the FFT data generator, which we have not written yet, we have to make sure that they stay in the same order. Okay, we also need to make sure that the blocks being sent to the FFT data generator is the right size. So let's create a mono buffer first for that. All right, let's go over to our header file. Put this right here. So this is what the buffer we are going to create now is what we will be ferrying blocks of audio from right to left through. So let me see. Let me just draw a quick graph of what I'm talking about here. Okay, so what I was saying about how the buffers need to be ferried from the right side to the left. So this is an example of like a waveform, you know, t equals 0 and then all the way to the end of it. Okay, so what happens is the buffers are passed to us from the host, and they, you know, that's what these A, B, and C blocks are. So what happens is we're given A, and then we need to basically, when we consume things with our FFT and our single channel sample FIFO, we're basically taking one of these blocks and then running it through that chain that I showed before. And then the whole thing needs to shift over this direction. Okay, so the A block gets discarded, right? It was just consumed by the GUI. And then what was in block B and C, they get shifted over like this. So you can see the continuity of this point right here to this point right there. Same for that point right there and that point right there. Here's the new data from the host. It's getting added to the waveform right here, so it's all continuous. And that gets, now we consume this part right here. Okay, then the same thing happens. This little chunk of audio gets run through the FFT stuff and is turned into a path, and then that gets consumed, and then the whole thing gets shifted over again. So that's why you can see that this piece gets shifted to block number 2, then it gets shifted to block number 1, and then it gets consumed. Okay, so that's what I meant about how we have to append the blocks to the end of it and shift everything towards the front of the vector. Okay, so we're going to implement that now. Okay, so we are going to need a mono buffer, because remember, these are mono channels of audio. Newest blocks are going to get stuck at the end, and the oldest blocks are going to go at the front, so that way everything gets kind of, you know, shifted over this way. Okay, step 14. All right, let's go back to our CPP file now that we have declared a mono buffer. All right, first we are going to shift everything in the mono buffer forward by however many samples there are in that temporary incoming buffer. Okay, so let's get our size first. All right, now let's do the copy. Okay, so we are copying everything from this point, which is size samples across. Let me pull this picture back up. Okay, so let's pretend that this is our mono buffer right here. It contains this waveform in terms of samples. Okay, our new chunk of data is going to get appended here. So what we need to do is basically copy all of these samples starting at position B, shift them over by however much this is, this direction. So that's what we do here. First we get, we're going to copy everything to the 0th index right there. And then we're going to start reading from this point, which is B. Okay, that's what this thing does. That's our index size. That's our index right there. And then we're going to read this many samples. So if our buffer is holding this long and we are going to read this many samples from it, that's how much we have to shift over. So we need to keep this much. Okay, I didn't explain that very well, but you can see from the code here what's happening. So once we have done that, now we can copy our temp buffer, copy all the samples from that to the end of our mono buffer. So our size, we're going to copy that many samples, put this on its own line. Our source is going to be the temp incoming buffer. It's going to be the 0th channel, 0th index. And we're going to copy it to our mono buffer, get right pointer, copying it to the 0th channel, and our sample index is going to be this position. Okay. If this doesn't make much sense to you, I suggest that you get out a line graph, draw a number line, and then, just like manually draw a block of data moving from one part to earlier in the chain to earlier in the chain, and data being added after it. And use varying sizes so you can see how how far we have to move it backwards. How far we have to move it towards the front is dependent upon what size of our block that is coming in is. Okay, so that takes care of those things, all right? We're shifting over the data, and then we're copying this to the end. Okay, and the good thing about this is that the mono buffer never actually changes size. So the next thing to do is to write the FFT data generator. However, if you remember what I said earlier, the FFT requires a specific number of samples in order to do its processing, so we must make the mono buffer have that same size. And this is good because we don't know how big to make the mono buffer for us to be able to copy into it and to move samples around in it. Like at this point, based on our current code, this is not going to work. It's going to explode because the mono buffer doesn't have any channels and it doesn't have any samples. So we're going to try to do like a negative, we're going to copy like negative samples and it's just going to explode. Okay, so once the FFT data generator is built, we will know what size to use for the mono buffer. So we're going to do that next. Once we are done with those two things, then we can start sending buffers from we can start sending mono buffers into the FFT data generator. Okay, so let's make this next. All right, this is going to go up here. All right, this is the FFT data generator. All right, let's take a quick glance at it. It's got a lot of good stuff in it. It's a pretty complicated piece of software machinery. Now, if you want to know how to build it yourself, I go through the entire process from scratch in the PFM Project 11 course. All we need to know for our purposes is how do we feed it audio, how do we get FFT data out of it, and then how do we configure it, okay? So let's do the configuration first. Configuration depends on this stuff right here. Here's how we feed audio into it, and then here's how we get our FFT data. And here's how we see how much FFT data we have available to us, okay? That's the basic interface. All right, let's give ourselves an instance of this after our mono buffer. All right, now the FFT data generator operates on vectors of floats, not audio buffers. Okay, let's go to our constructor so we can initialize this thing. Okay, go to our response curve constructor. Okay, we're gonna do this before we start updating our chain. All right, let's use an order of 2048. That'll give us some really nice resolution in the, that'll give us average resolution in the lower end of the spectrum. Okay, we're basically going to be splitting the audio spectrum up into 2048 or 4096, basically whatever value we pick from here. Okay, we can do 2048, 4096, 8192. Basically what we are doing is splitting up the audio spectrum from 20 hertz to 20,000 hertz into 2048 equally sized frequency bins. Now these bins store the magnitude level for a particular range of frequencies. I'm not going to get into the math behind this, but here's the simple summation. Okay, if we have 2048 bins and a sample rate is 48,000, then each bin represents roughly 23 hertz in our spectrum. Okay, so that's very simple math. If our sample rate is 48,000, and then we have 2,048 bins, each bin roughly accounts for 23 hertz. So that means we're going to get this means we are going to get a lot of resolution at the upper end and not a lot of resolution at the bottom end. So let's just take a look at our plot so you can see what I'm talking about. Okay, you can see that like, whoops. Yeah, this is what I meant about how it doesn't, let me comment out that code, this stuff right here. Let's comment this out. So this is what I meant, how like if each bin represents 23 hertz, between 20 and 50, between this part of the display and this part of the display, 20 plus 23 is 43. So that's how big one bin is way down here. Okay, but way up here, we've got 2,000 to 5,000. How many bins are there? Let's find out. So 5,000 minus 2,000, okay, divided by 23. There's 130 bins that are in between here. So we're gonna get a lot of resolution way up here, but not a lot of resolution down here. Okay, this is the big problem with FFT, but it's, that's just how it works, okay? So the lowest 5% of the frequency spectrum is going to represent 50% of the display, and the remaining 95% is going to represent the other. And it's going to represent the other 50%. What is that referring to? I am referring to where we've got 1 kilohertz is 50% of the display, from 0 to 1 kilohertz, and our range is 20 kilohertz. So that means this is 1/20th. From right here to right here, we cover 5% of our frequency range. And then this part, the other half of the display, is covering the remaining 95%, okay? So all this is saying that, we're gonna get a ton of resolution here, not a lot of resolution here. The only ways to improve that is to increase the FFT order. When you do that, the FFT ends up needing more and more CPU. So there's a nice balance between 2048 versus 4096 versus 8192 in terms of these, the order that the FFT is configured in, okay? That was kind of confusing, but basically when you make the order higher, you get more resolution in the lower end at the expense of more CPU. Okay, so we're gonna put it at 2048 frequency bins for right now, just so that way we don't have major performance impacts when we actually use this thing. Let's turn this back on. Let's go back to our constructor. And now we're going to configure this left channel FFT data generator dot change order. And we're going to do FFT order, FFT order and 2048. All right, now that our FFT data generator has been configured, we can initialize the mono buffer with the proper size. So we can do monobuffer.setSize. We are processing 1 channel, and our number of samples is whatever size this thing needs. Left get FFT size. We can uncomment these guys. These guys are uncommented. All right, now that we have this and the monobuffer is set up and the FFT data generator is ready to receive buffers, we can start sending monobuffers to the generator. So we can do left channel FFT data generator dot produce some FFT data. We're going to pass it the monobuffer, and we want to use negative infinity. We want to use our -48 as where negative infinity is, or we can change this value later. Okay, so let's check this out. I'll just put -48 because I want the bottom of my display, bottom of my spectrum analyzer, that grid point. I had set the scale to -48, so I'm going to use that right now for the concept of negative infinity. Okay, so let's build it and see what happens. All right, build failed. Why are we failing? Too few arguments. Expect to call. Aha! This is because our FIFO class needs a second prepare function to handle when the type is vector, not audio buffer. That's over here in our plugin processor. All right, it wants this. We are currently using this. Let's see what's going on. Prepare is declared here. We are instantiating it. Where is this being called from? It's being called right here where we've got a FIFO with our block type of, where was this declared? This was being declared with std vector. Okay, so that means this FIFO has a block type of std vector. Okay, and so obviously std vector does not have a set size function, so we need to create a new prepare function. All right, let's go do that. All right, let's use some static asserts to remind us if we are using, to remind us which prepare function to use. So we'll do static assert. Our expression is going to be std is same. There it is. All right, if our template type is t, we want to only use this prepare function if our t is audio buffer. So prepare num samples. Okay, it's helpful, helping ourselves. So check it out. If we build it now, static assert failed, so that's fantastic. Failed to meet requirement, and then we can see the message. It should only be used when FIFO. Okay, that's good times. And it says right here, instantiation of member std FIFO std vector. Okay, so we can help ourselves out that way. Let's write the other prepare function. Void prepare, and this is going to be size t num elements because vector uses size t internally. We'll do the same static assert. We'll change the message a bit. Instead of this, we will use std vector, and this should be num elements. Num elements should only be used when the FIFO is holding std vector float. All right, let's loop through this. We're going to go for auto buffer buffers buffer. Let's see, buffer.clear. Clear it first, then buffer.resize num elements and fill it with zeros. All right, now let's build it. All right, build succeeded. Let's head on over to plugineditor.cpp. Now the FFT data generator, let's go down to our timer callback. Okay, the FFT data generator is producing FFT data blocks for us. So now we need to turn those blocks into a path instance, okay? So let's write a path generator class. All right, let's go up to our header file. We'll go after the FFT data generator before the look and feel guy. Now this class is going to take in this FFT data, a bounding box, info about the FFT size and the bin width, and it's going to spit out a path, okay? Now this is a simplified version of the path producer in Project 11. So if you want to learn how to make the advanced version, check out the course. You're going to learn to make all this stuff from scratch by yourself. I'm going to give you the instructions and then review your code, which is pretty cool. All right, let's do this. All right, I'm just going to paste it right here. Okay, we can check this out in just a little bit. Okay, all we need to know is how to feed it our data via the generate path function, and then how to get paths out of it. That's what this does right here. Okay, so we've got our number available. We've got our function that gives us any paths that we request. And then here's how it actually converts that into data. So again, if you want to learn how to actually write this from scratch and learn how it actually works, this is a simplified version of the big one in the full course. Okay. All right. Obviously, we are going to need an instance, so let's give ourselves one of those. That goes down here. Analyzer path generator. We want to feed it JUCE paths, or we want it to produce JUCE paths for us, path producer. Now we can go back to our timer callback and use our familiar logic. While there are FFT data buffers to pull, if we can pull a buffer, let's generate a path, okay? So I'll just make a little comment to myself. If there are FFT data buffers to pull, if we can pull a buffer, generate a path. All right, very simple. Okay, now the path producer will produce a path inside of whatever bounding box we give it. Okay, let's just take a look at this interface real quick. All right, so we've got, it wants some rendered data. It's gonna want a bounding box, and it wants to know the FFT size, the bin width, and where negative infinity is, or what value is being considered negative infinity. Okay, so let's provide those things. So our bounding box is gonna be our FFT bounds get analysis area, and it wants it to be to float. All right, and it needs to know the FFT size and the bin width and frequencies. So the FFT size, as we showed in the constructor, we can just get it right from the constructor like that, or right from that FFT generator class. Auto FFT size. Oh, these should be const because they're not going to change. Okay. And then we need to know our bin width, and that's going to be, as we showed up here, our sample rate divided by our FFT size. Let me just copy this down here. Bin width. All right. So const auto bin width equals audio processor.get the sample rate. Divide that by our FFT size. Convert it to double because sample rate is a double. Okay, now we can implement our logic here. While left channel FFT data generator, while it has FFT blocks, whoops, right? If it has more than 0 blocks available, let's try to get one. Okay, we need a temporary vector, std vector float FFT data. Put past that here. All right, if we're able to pull one, then we can pass our vector of FFT data to our FFT data, to our path producer, sorry. Okay, one more time. So we're gonna check if we have more than 0 FFT blocks available. Good, if there are more than 0 FFT blocks available, let's try to pull one. And if we are able to pull one, this vector now contains our FFT data, which we can then feed to our path producer. Okay, so let's pass that along. FFT data. We know our bounds, that's that FFT bounds. We know our FFT size. We know our bin width. And we'll use that -48 again for the concept of negative infinity. All right, that should build without errors. All right, good times. Okay, I'll let you see this FFT, this path generator one more time so you can try to copy the code real quickly. Scroll down a little bit. You can just pause the video if you need to see it. Good times. Same for this one right here. All right, there's the path, there's the data generator. Okay, all right, so this builds currently. We are almost there. We just need to retrieve these paths and then draw them. All right, go to your plugin editor.h. Okay, go down to after where we added our path producer. All right, we have, at this point, we are producing paths in our path generator. Now we just need a path to draw and to pull into, okay? Because remember, we're pulling it from the timer callback. We need to get it into our paint function, so it needs to be a member variable. Choose path left channel FFT path, okay? That's makes sense why we have that. All right, let's go to our plugin editor, back to our timer callback. So at this point, path producer has potentially created a path for us. So we need to try to pull them. Now, what happens if we are producing paths faster than we can consume them? We just want the most recent one. So our logic is going to be, while there are paths that can be pulled, pull as many as we can, because we're only going to display the most recent path. All right, so while path producer get num paths available, now we can do path producer get path, and we can use our left channel FFT data path. Okay, that has successfully pulled that path. Now, previously we were only repainting whenever the parameters were changed, but because we're pulling paths all the time, we need to repaint all the time. So this gets commented out. This goes here, repaint, like that. All right, now we just need to paint the actual path. Let's go to here. All right, let's go to our timer. Let's go to our paint function, and let's draw this. Where are we going to draw this? Let's draw this before we draw our, where is this? Let's draw this before we draw our rendered area, so it's behind everything. Okay, I'm going to use a blue color. All right, and we can just do G stroke path, left channel FFT data, FFT path, and then I'm just going to use a path stroke type with a thickness of 1, and let's run it. should see something. Oh, my fault. What is going on here? I spelled that wrong? I did spell that wrong. Okay, let's run this. Not as the standalone, but as the plugin. As the plugin in the audio plugin host. Okay, we should see something once we actually press play. Okay, all right, we have a blue line. What happens if we actually run audio through this? All right, it's doing something. See that up, turn that on. Okay, cool, that is an FFT, that is a spectrum analysis. Okay, now it's in the wrong place, but it is working, which is awesome. So we can fix that positioning next. Let's make a commit of that, because that was a lot. All right, implemented basic FFT design. Okay. Of course, in the description, I will have the links in the description. The links in the description will there will be a link to this repository, so you can check out the code for yourself once this video is out. And then you can get the code for the single channel sample FIFO, the FFT data generator, and the analyzer path generator. Okay. All right. Now there's a small bug right here with the way this stuff is getting mapped. We are currently mapping from, we're mapping our bin frequency from 1 to 20 hertz, but our frequency range is not 1 to 20 hertz, it's 20 to 20 hertz. So that's the first bug fix we need to do. Okay. If we run this and check it out, it should look a little bit different, or the X positions should look a little bit different. Okay, now it's hard to tell, but basically we weren't seeing a lot of left stuff on the left side. Okay, so that's good time. All right, let's close that. Let's save this so our parameters are saved. And if we want, we can use a different color to make the path more visible. It's, that blue color is kind of hard to see. Okay, let's start making this show up in the right spot. Okay, let's go to our paint function. Okay, now when the path generator creates a path, it does not take into account the origin of the rectangle that defines the bounding box. So we need to translate our path to the analysis bounding box's origin. Okay, right now this path is drawn at 0, 0, and we need it to be drawn at our response areas X and Y. That needs to be the left side of the path. Okay, so we need to do a translate first. So let's do that right here. Left channel FFT path dot apply transform. So we're going to do a normal affine transform, and we're going to add a translation to it. So we want to do response area dot get X and response area dot get Y. Okay, what does that do if we run it? That should be all we need to do. Okay, cool. This is like right on the -48. So let's push play. Cool, so it's now drawing in the right spot. I'm gonna use I'm gonna use like sky blue or something for this instead of that dark blue, so we can see it a little bit better. Oh, what happened here? Oh, there's a bug for that. That's right, it's gonna do that for a while. For some reason, we'll figure it out. The FFT data is just full of nans. I'll just comment that out for right now. Okay, let's press play. All right, that's easier to see. That's all I was trying to show. Okay, cool. All right, we'll figure that out in a little bit. All right, let's make a commit showing that we fixed the positioning, because sometimes those types of bugs will take a long time to diagnose and then solve. Okay, so fixed FFT path position. Stage that, stage that, stage that. Okay. Next, we need to verify the accuracy of the analyzer. Now, to do this, we are going to go to our plugin processor.h. We are going to, we're going to switch to the standalone version. And then we're going to use an oscillator to do this, and we need to initialize it, prepare it, and then use it in the process block. So we're going to feed it a test signal. Let's go way down here, way down to the bottom after our update filters. So JUCE DSP oscillator float like that. Okay, that is now declared. We're going to make this produce a sine wave at a particular frequency, and we want it to line up with our we want it to line up on our grid where it should. Okay, so let's go to our, where do we go next? We need to prepare it. So let's go to our prepare to play function. Let's do this at the end. The oscillator wants a function that returns a value when you feed it a radian angle. Okay, so std sign wrapped in a lambda will do that for us. So oscillator.initialize. Here it wants a lambda that takes in a number and returns a number. So let's do that. Here's our number that it's going to take, and then here's what it's going to return. Okay, now we need to prepare it, and we can use the same spec for our chain as long as we just change the number of channels. Okay, previously we were given, we were saying our spec only had one channel. We just need to change that. Spec.num channels equals get total num output channels. Sure. And then we can prepare it. Osc.prepare the spec. And then let's give it a frequency of 200 because that's one of our points in the grid. Osc.set frequency. We'll be changing that frequency for a while just to verify the accuracy. So I'm going to go with that value, 200 initially. And let's see what comes next. All right. Let's go to our process block because we want to use our oscillator to fill the buffer. Okay, so we're going to do this before we're going to do this after our filters are configured, but before we actually run the sound through the filters. We don't want to hear any of the audio that's currently coming in, so we'll do buffer.clear. And then we need to make a stereo context and then give it to our oscillator to process. That's all we have to do. So let's see. This block is already stereo. So let's see. I'm going to move this after this thing. Okay, buffer's clear. Let's make our stereo context for this block. Stereo context from the block, and then now we can just do osc.process stereo context. All right, that's it. Okay, and we can now check the accuracy. So apologies in advance for the annoying sine waves we're going to hear. Okay, so our frequency was 200. So let's try 500 and 1,000 and 50 and 5K and see what it looks like. So I'm going to change this to 1,000. We should see a little blip right at that point. All right, that's good for me. 1,000. Let's do the annoying one, 5,000. Yep, right at 5K. Yikes, that's painful. Let's make this 50. This will be the last one that we test. All right, I'm not seeing anything at 50. So let's try 100. All right, there's our 100. Okay, so 50 was pretty low for some reason. It's pretty accurate. It's showing a peak at 100. It showed a peak at 200, 1K, 5K. Okay, so that's good times. If we want to do more resolution in the lower end, we could just change the order of the FFT generator, but this is good enough for this project. Like we're just trying to get our feet wet and understand how some of these things get put together in audio plugins. So the next thing to do is to add a second set of generators that can produce a path for the right audio channel. All right, let's get rid of our, let's get rid of that process block stuff, this stuff right here. Let's just comment that out in case, we're gonna leave the code in case we ever need to test that again. But that's, we're gonna turn that off because who wants to listen to those sine waves again? Okay, let's grab everything we used in the single channel version of the FFT and put it into its own class. This is going to be the single channel FIFO buffer, the mono buffer, FFT generator, analyzer path generator, and the path itself. So let's make a new class. We're just going to migrate these things over there first. Okay, so I'm just going to cut these. I'm going to go up here. We're going to put it right here. Put them right there. All right, so we have moved those over. Okay, this is going to produce a ton of errors if we try to build it right now, but we will get to that. Now we just need to give our response curve a path producer for both channels. Okay. Next, we need to add a process function that's going to basically do what the timer callback did. Let's jump to that so we can kind of get a feel for what I'm talking about. This process function is going to do this, it's going to do this stuff, and it's going to do this thing. Okay, so let's declare that first. Actually, let's take a look at this. So let's see, right now, the only things we actually need from it are this temp buffer, FFT bounds, and FFT size, and bin width. Yeah, okay, so we just need, and even then, like this FFT size comes from this member variable. FFT bounds, that's just a rectangle, we can provide that. And then we need the sample rate. Okay, so let's do that. Let's go back here, let's declare this. Let's make these guys private. Private. Void process, let's give it our rectangle and the sample rate. Okay. Now we need a way to retrieve the path. So let's add that. Okay. All right, now we need to do what the response curve constructor did to initialize the FFT data generator and the mono buffer. So let's add a constructor. All right, let's go add a constructor. We'll just do it in class for right now. It's going to take this same argument, SCSF. All right, let's initialize that. Left channel FIFO, SCSF. Okay, now let's just migrate over that code from the constructor over here. Where was that? That's this thing. Okay, we're going to just grab these two lines, cut them, paste them here. All right, now we just need to initialize our path producers from our response curve. So let's get rid of this line, and now we can do path, left path producer, and this is where we need the audio processor left channel FIFO, address of that, or not the address, it wants a reference. And then right channel path producer, this wants the audio processor right channel FIFO. All right, let's implement this path producer process function. Let's put that right above our, right above this. Actually, let's just put it right above this timer callback because it'll make copying the code easier. So void, we can move it later. Path producer process. Okay, so we need our temp buffer. These guys just go like that, copy and paste it. Do the same thing with the FFT bounds and through the path producer loops. And now instead of doing auto FFT equals get analysis area, this is a function argument. So let's get rid of that. And then our bin width is using the sample rate. Okay, very convenient. All right. So we took all of that code away, and now we are going to call our process function instead. We will do auto FFT bounds equals get analysis area dot toFloat. And then auto sample rate equals audio processor dot get sample rate. And then we can do left path producer FFT dot process FFT bounds sample rate. And then right path producer process FFT bounds sample rate. Now we just need to grab the paths returned from this in our paint function and draw them. So let's go up to our paint function. Go to where those paths are drawn. That's right here. We will do auto left path FFT, left channel FFT path equals left path producer dot get path. Okay, that takes care of that. And then we can also, let's see, we're doing sky blue for that. That's cool. And now we can do the same thing with the right path. Auto right channel FFT path equals right channel get path, and do the same transform, and then draw it the same way. I'm gonna do yellow for this guy. I'll do light yellow. All right, let's test it out. We should be able to see two analyzer paths. Actually, this is the standalone version, so let me quit this. and then run the VST version. And now we can run some audio through it, and it should be good to go. Okay, let's press play. We should hear some audio. All right, cool. So I'm not seeing two paths. So the solution. Well, I'm seeing a yellow path. I guess our file is this file that I'm using is fairly mono. Cool. The left channel and the right channel have similar signals, which is good. Okay, so something we could do to fix that is to open this up in an actual DAW and then open it up in a DAW and just feed it a channel only on the left side. We can just go like this. Disconnect this side. Nothing's being passed. Why is that only doing that? Interesting. So we're not seeing our right channel for some reason. All right, let's see if we can figure that out. I found the error. So the problem was I was drawing the left path twice. That's all. It was pretty dumb, pretty stupid error. That's what I get for copying and pasting and not being thorough. The way I went about actually trying to debug it was going over to my plugin processor. And then in my process block function, I'm going back to using my test oscillator. And I'm clearing the buffer and I'm writing the oscillator's samples to only one channel, particularly the left channel. And then from there, I was just checking to see like, hey, is this actually getting proper audio? So it turns out it was. And then after looking at all the other code that was copied over, it literally was just me drawing the left path twice. Okay, so let me go turn off this code right here. And then let's run this in the VST, and let's run this in Audio Plugin Host, and we should see both the left and right channel. All right, let's try this again. All right, definitely have a blue and yellow line. That is fantastic. And if we roll off the high end, all the high end stuff disappear. Same for rolling off the bottom. We get to see our frequency response after the effects of our EQ. So let's do a big cut. You can see that get dipped out as well. All right, cool. Okay, that's the analyzer. We can check that off. Make a commit of that. Right. Implemented FFT spectrum analyzer. Okay, let's just stage all this stuff and commit. Okay, so the next thing that I want to add is some bypass buttons for each band, and then a bypass button for the analyzer because those analyzers always use a ton of CPU. Okay, cool. All right, time for the bypass buttons. Now we have 3 bands, and thus we need 3 Boolean parameters to enable bypassing each individual band. And I also want to be able to turn the analyzer on and off, so we're gonna need a Boolean parameter for that. So head on over to your plugin processor and go down to where your parameters are created, and we're going to add some Booleans for this, okay? Layout.add, std make unique, and we want JUCE audio parameter bool. I'm gonna call this guy LowCut bypassed, and a default value of false, meaning that they are not bypassed. All right, we're gonna do 2 more of these for the parametric band, peak band, whatever you want to call it, and the high cut. Okay, and then 1 more for the analyzer to be enabled. And this one's going to be true, meaning the analyzer is enabled by default. Okay, let's go over to our plugin processor.h because way up near where our chain settings are defined, we need to supply the bypass states at the same time. So let's add 3 Boolean flags to represent that. Boolean LowCut bypassed, false. Peak bypassed, false. And then high cut bypassed, false. Let's go back to our plugin processor.cpp. Let's go to where we get our parameters, get chain settings. And this is where we need to grab these guys. Now these are Boolean parameters, but the parameters are stored as floats. So if the value is greater than 0.5, that means it's true. So we can do settings.LowCut bypassed equals, then get the parameter LowCut bypassed. It's atomic. If it's greater than 0.5, then it is bypassed. All right, do the same thing for the other two parameters. Okay. All right, let's go to our update LowCut filter function. Now, all we have to do here before we update the cut filter is set that bypass state. So left chain dot set bypassed, and then chain position LowCut, and then chain settings LowCut bypassed. All right, do that for both chains. Whoops. Copy, paste, right chain. Do the exact same thing for the high cut. All right, we want the high cut position and high cut bypassed. Then finally do it for the peak filters. Well, let's just copy this line. Left chain to set bypassed. Peak. All right, that takes care of the DSP. Our chains get updated with the bypass settings. Now we just need to add some buttons to the GUI. So let's go do that next. Head on over to the plugin editor.h, and we're going to go down to our editor, and we are going to add some toggle buttons. Okay, I'm going to use toggle button for right now because we can customize those visuals later. And this is just going to do the job for right now. All right, I did all four: low cut, peak, high cut, and then the analyzer enabled button. Now let's go to our plugin editor.cpp. We're going to go down to our get comps function. We're going to add those 4 buttons. All right, now we need to position them. So for this, let's go to our resized function. Now I want to give them a height of 25. I want them to sit above each of these stack of knobs that we got, the stack of sliders. So we've got our low cut area, our high cut area. So at the top of those is where I'm going to put this. Okay, so let's do the left side first with the low cut. Low cut bypass button, set bounds. And we're going to do low cut area, remove from top 25. All right, we'll do the same thing for the high cut bypass button, set bounds, high cut area, remove from top 25. And then our peak bypass button, let's set bounds, equals bounds.remove from top 25. Cool. We are going to do the we're going to do the analyzer button in a little bit, but we have these 3. Let's take a look. Put it on the standalone version for right now. You should see 3 buttons right in the middle, centered among the 3 columns of sliders. And there we go. Here's our toggle button. All right, cool. Let's connect them to parameters next. All right, go back to plugin editor.h, and we need to declare some button attachments. So using button attachment equals APBTS button attachment. And now we can declare 4 of them. Just gonna copy these guys and then put attachment at the end. If I put them all in the same line, it'll make it real easy. Or if I line them all up, then I can do this. Cool. All right. So those are the attachments. We're going to use them the same way we did with these sliders. We just need to connect them to the actual parameters. All right, we go do that in our constructor. Plugin editor constructor. At the end of this list, this is where we need to add the attachments. Low cut bypass button. It's this thing. Low cut bypass button. And then the parameter ID is low cut bypassed. All right, and we needed to do this for the other 4 buttons, even though we're not showing the analyzer. Peak bypass button. Okay, let's give that a quick build. Make sure we don't get any errors. And let's run it to make sure that we typed our param names correctly. But those should be connected now. All right, so let's run it. All right, let's run it with audio plugin host so we can run audio through it and see if we hear it do anything. Okay, so I'm gonna set this up kind of high, run some audio and then bypass. All right, so the bypass control definitely works, but the response curve is not updating. Okay, let's take care of that next. All right, let's head on up to our update chain function for the response curve component. Now we've got our chain settings right here. So we're going to do the same thing we did with the process block. We're going to update the bypass states of the chain accordingly. Mono chain set bypassed, and then each of the indexes: chain position, LowCut, chain settings, LowCut, bypassed. All right, do that for the other 2 chain positions. Okay. All right, once we've got these bypass states, let's go to our paint function. Because once we have these bypass states, you know, if the chain is not bypassed, we need to add the magnitude. However, for the low cut and high cut bands, even though we bypass the entire chain, this right here does not check if the actual link in the greater chain is bypassed. So we need to do that for these guys. We need to do if mono chain.is bypassed. All right. If the low cut processor chain is not bypassed, then we can check if the individual bands are bypassed. We can do the same thing for the high cut. All right, let's test it out. Oh, got this JAssert that's happening. We'll take care of that in just a little bit. For some reason, the render data is full of invalid values. Let's show me my plugin GUI. All right. All right, look at that. See if it does it for this one. That's bypassed. All right, cool. Let's do it for this guy. All right, awesome. That is working as expected. All right, let's make a commit that we have added bypass buttons. Added ability to bypass DSP bands. Response curve follows bypass state. Good times. All right, we can dial in the graphics next. Okay, for this, we want to use the toggle button look and feel function, draw toggle button. Let me pull up the documentation for that. So look and feel methods version 4. Let's see, these are slider. We want to look for toggle button. Where is that? Where are those look and feel member functions? No, it's part of the look and feel class. Okay, so we've got draw button text, draw toggle button, draw tick box, drawable button, all that kind of stuff. Okay, so we want to implement draw toggle button. So let's go up to our plugin editor.h. Let's go to where our look and feel is declared. And we're going to add this draw toggle button function. Just going to grab it from the documentation. Give me some names for these guys. Let's put them on their own line. And then all these need that JUCE namespace before them. Okay. All right. And after these look nice, it would be wise to make the toggle buttons actually disable the sliders for whatever band they are attached to. So that's going to be one of the things we're going to work on as well. All right, we just need to give our editor a look and feel instance. All right, and we need to assign it to the 3 bands. We'll do that in our constructor. Go down here. Let's do it after we add and make our guys visible. Peak bypass button dot set look and feel. Low cut. And then we need to set these to null pointer in the destructor. Cool. All right, let's go to our look and feel implementations. plugin editor.cpp. Go to where that look and feel implementation is. It's way up at the top. All right, let's clean up this space. Now, right here, what I would like to create for these toggle buttons is a power button type of graphic, and this can be accomplished by using the path function add centered arc. Now, this function will let us create an arc which has a notch at the top, and then we just need to add a vertical bar that goes from the top to the center, and that's it. Okay, it's super easy. Just use a wide stroke type when it's time to fill the path, and it will look like a power button. So let's do that. All right, using namespace JUCE, because I didn't turn it on in ProJuicer, ProJuicer. That setting is here, by the way. If you go under your gear, then you can do add using namespace JUCE to the JUCE header.h. It's disabled by default because the thought is that you're less likely to get collisions with other namespace classes, such as the point class, which is a default class on. It's one of the classes that comes with some of the OS X frameworks. So by turning this off, it makes it less likely that you're going to get those types of namespace collisions with your class names. Okay. All right. Enough of that. Let's see. Path power button. Okay. First thing first is we are going to create a rectangle. This rectangle is going to have equal length sides, and in the center of that will be our this rectangle is going to be center in our components bounding box. So let's do that first. Where's our toggle button? We're going to do that same jmin thing that we were talking about. We did that up for the, we did that somewhere. Somewhere we did a jmin, so that way our, one of these rectangles was a square inside of a non-square bounding box. That right here, this is where we did it, in the get slider bounds. Okay, we're doing that same thing right here. All right, so instead of it being exactly a square in the center of it, we're gonna shrink it a little bit, maybe like 6 or so. We'll use juice live constant to figure it out later. Maybe we'll do 4. No, I'm gonna go back to 6. If I want to adjust it, I can come back with juice live constant and tweak it that way. All right, and then auto r equals bounds.width size, keeping the center. So I'm creating a rectangle with this size, whose center is the center of our toggle buttons bounding box. All right, now let's specify some angles to make the gap at the top of the arc. Okay, we're gonna specify some angles to make the gap at the top of the arc, and then we're gonna shrink this square to be drawing. We're gonna shrink the square just a little bit more. We'll play around with it and with juice live constant, and get it to look the way we want it to look. So float ang equals 30.f because it's radians, because I don't know how, it's degrees because I don't know how to think in radians. We'll shrink this size a little bit, maybe just a little bit more. We can use juice live constant later. Now let's make our arc power button dot add centered arc. Okay, so we're gonna center it at R. Our radius is going to be half of the size of our box that we have. Size times 0.5. That's the radius for both axes. All right, we're not rotating this ellipse at all. So that means that 12 o'clock is still going to be right here, as opposed to if we had rotated it, then it would be like negative 30 goes to here and plus 30 goes that way. Okay, so we are going to do 0 for that. And then our from radians, let's see, if this is 12 o'clock right here at the top, I want to go negative 30. Or no, I want to go 30 this way, and then I want to go 360 minus 30 for the second one. So here we go. Let's see. Radians. Degrees to radians, and we've got 30, or our angle. And then the same thing, degrees to radians. 360 degrees minus our angle. So if we want, we can open this up. There's no, we're using these variables so that way we can adjust the way these visuals look. And then, yeah, this says there's an extra, let's see, power button.add centered arc. There's an extra parameter that's not shown up here. Start as new subpath. So this is the parameter I want to add. This should be true. All right. Now let's make the vertical line. Okay, power button. Start new subpath. And this subpath is going to be, it's going to be at the center of our rectangle, but then at the top. And then we can do a simple power button dot line to r.getCenter. So we're going center of our box, at the top, y equals 0, and then we just go straight down to the center. All right, let's just create a path stroke type of 2. Normally when you draw a path, you can do JUCE. You can do g.draw path or stroke path like that, and then provide a stroke type that way. But I want to specify some custom stuff, so it will help me if I use the path stroke type constructor. This one right here, so I can use that joint style. Okay, so I'm going to use a stroke thickness of, we'll try 2. And then for the joint style, if I use a curved joint style, it'll give me rounded edges at the gap and then around that rectangle. So I'm going to use that. So I'll do curved. All right, now this just needs a name, PST, and now I can use that here, PST. And then the path is going to be the power button. And then what is wrong with this? Why is this complaining? Oh, is that because that needs to be to float? Yes, this should be a float rectangle. Now we just need a color. So if the button is on, we're going to use one color, and otherwise we're going to use another color. So what that means when the button is on is that the band is bypassed. Okay, so if it's bypassed, let's use a gray color. And then if it's not, let's use that green color that we've been using in other places because it looks cool. All right, so let's see, auto color equals button.getToggleState. Oh, sorry, toggle button.getToggleState. Get the toggle state. If it is on, meaning the band is bypassed, we're going to use colors dim gray. Otherwise, let's go find that green color. I think that's this. I should really standardize that, but you know, it's a tutorial. I'm not trying to show the best practices, but I'm trying to show good practices. Okay, here we go. G.setColor, color. All right, so we're going to draw our path. And then we can draw a circle around the whole thing once we draw our path. G.draw ellipse, and we can do R with a line thickness of 2. All right, that should look good. All right, let's try that out. Hey, look at that. Okay, cool. So these are currently not bypassed. So I'm going to adjust this and then do that. So that's cool. That works as expected. If it's green, it means it's active. If it's gray, it means it's not. I'm happy with that. That makes sense. Well, that's kind of interesting. As long as we're clicking inside the bounding box, it's going to toggle it. So something that we could do that I'm not going to do here is to set up the hit test region. So that way, if you only click inside this area, it says, yes, you clicked on me. Otherwise, if you click out of that, no, we did not click on you. So for reference, I'm going to just add a G.setColor, colors red, and then G.drawRect, just so we can see the bounding box I'm actually talking about, bounds. So this way you can see what I mean about if you click outside of it. Okay, so if we click anywhere in here, we are technically clicking inside that toggle button. Okay, but we only want to, it's not something I'm going to do in this video, but we could go through and say, you know what, it's only when you click inside this. There's a special hit test function that we can override and say, if we click inside here, that means we actually clicked on the component. If we clicked here, we did not. And that's how we can make it only respond that way. But I'm not going to do that. It's a little bit beyond the scope of this tutorial. So I'm just going to get rid of that. Okay, let's add a commit for that. So customized the graphics. All right, before I do that, actually, I wanted to show the juice live constant thing. So if we do this here, juice live constant, this was 6. Same for this one. This was also 6. And we can mess with this angle too. All right, so this will be interesting. We can see what that looks like. Let's change these numbers, move these sliders. We'll get to see what it looks like. All right, let's move this out of the way. So we're changing the first one. This is going to make these guys get smaller or bigger. And obviously, once we get past a certain point, they start being drawn outside their bounding box. Now here's where we can adjust the angle. So that's kind of neat. All right, so I like where we had it. Maybe 40 or 40 looks kind of cool. Maybe a little bit closer, like 25 is good. And then this one, this shrinks that guy a little bit more. So it's like this one changes the whole thing, and then this one changes that inner arc. All right. So I'm going to leave those where I had them because I liked that positioning, but you can do that same thing to adjust the placement of those guys. All right, we'll put this back to 30, put this back to 6, and put this guy back to 6 as well. All right, cool. Let's make that commit. All right, now what I want to do is reuse that toggle button functionality for the analyzer button as well. Let me say that again. What I want to do is reuse this toggle button. I want to reuse this draw toggle button functionality for the analyzer button as well. But what I want to do is switch based off of the button type in that draw toggle button function. So I'm going to create 2 classes. I'm going to go here in my editor. I'm going to do this right above the editor. I'm going to create 2 classes that inherit from toggle button, and that's going to allow me to cast between the. It's going to allow me to cast that let me see. Let me go up here. It's going to allow me to cast this argument to determine if it's one of these 2 types of buttons, and then I can switch accordingly in the actual implementation of that function. Just follow the code. You'll see what I'm talking about. I'm not explaining it very well. Here we go. Struct power button, juice. Okay, very simple. Struct analyzer button. Okay, so that's step 1. All right, step number 2 is to make the bypass buttons. We'll make the bypass buttons become that class. Power button. And then the analyzer button needs to be an analyzer button. Like that. Okay, very simple. All right, now let's go up to our draw toggle button look and feel implementation, this guy right here. All I need to do is just cast, and everything should work as it did before. Okay, so I'm just gonna have this power button path. I'm gonna cast, gonna make a check, and if like I can cast this object to a power button type, then I'm going to do all of this. All right. If auto. Okay, so if we run it, I'm going to put this back on the editor, on the standalone version, because it opens a little bit quicker. We should be able to run it, and now we can add code that draws the analyzer button after this is verified. All right, sure enough, we still have our analyzer buttons, our bypass buttons working as expected. Cool. So let's add our analyzer code. Where is this being added? Okay, we're going to add our analyzer code here. Now, I think it would be cool to see a randomized path drawn inside of this button to kind of, reflect the fact that it is an analyzer. So I'm going to use the same color settings that I used for the power button. Green if something is active and gray if something is not. In this instance, the toggle button will reflect the opposite state that it did with the power button, which means I cannot use this thing. I have to flip it around. So let me add an if else or an else if right here to make sure I have an analyzer button. Go faster if you're walking. Copy this color line over. And we need to flip that. That's all. Because as I said, if the toggle button is on, then that means we want to use this green color. Otherwise, if it's off, let's use the dim gray. All right, g.setColor, color. Okay, next I'm going to start by drawing a normal rectangle, auto bounds. Now I'm going to shrink it a little bit. And then I'm going to randomly generate a path inside of that smaller rectangle. I don't want it to look too crazy, so I will produce a line segment every other pixel. So let's start with our path, random path. We'll use a random object. And then now we can start our random path. We will start it at our inset. And our y position will be inset rect.getY plus inset height times some random float value. All right, so our y value is going to be the top. Our height is the bottom. So we're going to go, remember this is 0 and this is height. So we're going to go 0 down to height, multiply height by some value between 0 and 1 to give us a random height between the top and the bottom. All right, now we just needed to perform a line 2 like this for auto x equals inset rect.get x plus 1. X is less than inset rect.get right plus x plus equals 2. Then we just basically do this. Our x position is going to be, let's see, this is going to be line 2. Oh boy, line 2. Come on, get out of here, Trixie. Let me just type this line. Random path, line 2. Our x is going to be x, and then our y position is going to be this. Obviously, we should pre-cache some of these positions, because calling get y and get height every line is, it's not ideal. But whatever, we can always refactor that type of stuff later. Okay, now let's just draw the path. Let's use a thickness of 1. All right, that should do it. Let's get our analyzer button on the screen and using this look and feel so we can tweak this if needed. Head on down to our editor constructor. Let's provide that look and feel. Analyzer enabled button, set look and feel. All right, and don't forget to disable it. All right, now I'm gonna stick this right at the top of the GUI on the left. So let's see. I'm gonna go like this. I'm gonna go auto analyzer enabled area equals bounds.remove from top. Give me the top 25 pixels, just a whole row, 25 pixels wide, 25 pixels tall from the very top. Okay, now I'm going to do analyzer enabled area dot, give me a width of 100. Give me an X of 5, so it's not right along that edge. And then just remove a little bit from the top of this analyzer enabled area so there's a gap between the top of the GUI and the top of this rectangle. All right, now I'm just going to set that to be my analyzer enabled button's bounds. And let me give myself a little bit of a gap between the analyzer button and the analyzer itself, and let's see what it looks like. Bounds.remove from top 5. Okay, so we should expect to see a squiggly line just like that. All right, okay, this is neat. So whenever we mouse over it, it repaints and it produces a new path. So let's make the path be a member variable of the class that is computed only once whenever the instance is resized. So we know that our random path creation process works, which is cool. So we're just going to use that to make this path. All right, let's do that next. All right, let's add a commit for this. Analyzer button is visible. Path is created every time it repaints. All right, let's head on over to our declaration for that class. There it was here, analyzer button. All right, so let's set this up with a resized function. This is where we will compute the random path that the toggle button will draw. So let's see, void resized override. All right, we're gonna need those bounding box. We're gonna need that bounding box, auto bounds equals get local bounds. We're still gonna need to shrink it. And then instead of creating a new random path, we're just gonna clear the existing one. Let's add that as a member variable. JUCE path random. All right, So random path.clear. It's going to clear it. And then let's go grab our other code that drew that thing that's way up here. That look and feel stuff. Where is that? This stuff. All right, let's just copy this, comment it out, plug in editor, paste that right here. Okay, here's our juice random, except it needs to be a juice random. All right, there's our random path, start new subpath. Same line 2 code that we had before. All right, let's go back to our plugin editor. Okay, so the stuff we need to discard is the inset rect. The random path, we can get rid of that. And now for this, we need to write analyzer button, oh boy, random path like that. Okay, so we're just gonna draw that path member variable directly. All right, let's run it and see what we get. All right, cool. So it's only changing right now. Let's open, it only changed once when we used the standalone. Let's open this guy. I'm gonna run it in audio plugin host and see what happens when we open and close the GUI. Okay, so there's like an M right on this right edge. Let's see what happens when we close this GUI. All right, that's kind of neat. So every time we open and close the GUI, we get a new path, which is, you know, it's kind of neat. Okay, so the next thing to do is to make these buttons actually disable elements in the GUI. All right, when we click on this, we want these sliders to stop working. When we click on this, we don't want to see the FFT happen in the background. Okay, we will do those next. Let's leave this open. All right, let's get rid of this code and make a commit. Analyzer path button. Analyzer button path is created only once. All right, now if we were real sticklers about making it only appear once every time the GUI is opened, what we could do is store this path. It could become not an audio parameter, but it could be stored in the audio parameter value tree state value tree. It could be stored as like just binary data, and then that way whenever the plugin is first created, you get a customized path, and whenever you load that in, it gets stored with the plugin. So that's, you know, that's a way to make it not have not be, it's random the very first time you open the GUI, but that's the only time. Once you have to create a new instance of the class or a new instance of the plugin in order to get a new path there. But you know, this is cool. All right, let's see, what are we gonna do? We are going to make our buttons actually enable or disable GUI parameters next. Okay, head on over to the audio processor editor constructor, and we're gonna go down to after our look and feel has been set. Now we are going to use the on-click lambdas to change the enablement of the sliders. So the reason I'm doing this here is because this is where all of these components can see each other. All right, I'm gonna make this button control these. This button is gonna control this slider and this slider. This button is gonna control these 3 sliders. This button is going to control the high cut buttons, this guy and this guy. And then this thing is gonna send a message to this thing to stop drawing the analyzer. Okay, so that's why we're doing this here instead of like inside, maybe we make some macro component that owns the sliders and stuff. I'm doing it here because this is where the most common place, this is the place where all the components can see all the other components. So it makes just the communication between them easier. Now, as with all asynchronous callbacks, we need to use a safe pointer to make sure that our class, in this case the editor, is still in existence when we try to use this particular on-click lambda. All right, so let's get started with that. Auto safe pointer equals juice component safe pointer simple EQ audio processor editor. This. All right, now we can start declaring these guys. So we'll start with the peak bypass button. And this is where it wants a lambda with no arguments. And here's where we're gonna do the good stuff. Okay, first we have to check if our safe pointer exists. So if auto, all right, if it does, once we know it exists, we can get the bypass state and set our sliders enablement accordingly. So auto bypassed equals comp peak bypass button to get toggle state. Easy. All right. Now remember, if the band is bypassed, that means the sliders should not be enabled. Or said in reverse, if the band is not bypassed, the sliders should be enabled. So comp peak frequency slider set enabled. It should be enabled if we are not bypassed. Okay. Let's do it again for the other sliders. This is the peak gain and the peak quality. All right, let's test it before we make the other bypass buttons work. All right, we did the peak one. I'm not seeing it do anything. Let's go up to our look and feel. All right, so here's our draw rotary slider. What are we not doing? We are not setting our colors differently if we are enabled or disabled. So let's go up and do that next. All right, we can do that right here. Auto enabled equals slider.isEnabled. Now we can set these colors accordingly. So if we are enabled, use this cool color. Otherwise use, let's go with the dark gray. That's for the background circle. Same thing here, enabled. If it's enabled, use that, I guess it's an orangey color. It's the border. So we will do colors, a different type of gray. All right, do we have any other colors that are displayed in here? Looking for set color. That's for the text. All right, let's try that out one more time. There it goes. Awesome. Okay, so I would like the parameter text to also fade out, but we can do that after we get these other lambdas set up. So we're gonna follow the same pattern. Let's go back down to our constructor. We're going to follow the same pattern. We're going to capture a safe pointer. We're going to check if the component is valid. And then if it is, we will get the bypass state and then change the enablement of the sliders accordingly. So let's do the LowCut next. LowCut bypass button.on click. All right, first make sure the component is valid. If it is, get the bypass state. All right, this is the LowCut bypass button. And then set the LowCut frequency slider. Remember, it should be enabled if our button is not bypassed. Okay, and then same thing for the high cut. All right, let's give that a test and see what's going on. See if it's working as expected. This is high cut, high cut, high cut, low cut, low cut, low cut. Okay. All right. Awesome. Cool. Let's add a commit for that. Oh, I forgot to commit these guys. All right. Commit those. Let me say, let's see, bypass buttons, toggle slider enablements. That's what happened there. And then also, yeah, that's all part of that same thing. All right, our next step is to make the analyzer button toggle the FFT analysis, the spectrum analyzer. See if make that do something. All right, so let's go right here. We're gonna do analyzer enabled button on click. We're gonna capture the same safe pointer. If auto comp equals safe pointer dot get component. All right, now we need our enabled state. All right, and now let's call a function that doesn't exist yet. We'll add it in just a second. Comp response curve component dot toggle analysis enablement enable. Okay, that's a good name for what this function needs to do. All right, let's head on over to our header file, editor.h, and provide that function so we stop having that warning. Okay, that's, where is that? Here's our response curve component. So void bool enabled. Okay. And now, let's see, what do we need to do? We need to have a flag that it can check. So let's put that down here at the bottom. Bool should show FFT analysis. We'll set that to true by default. And then we'll just do an implementation in class. should show FFT analysis equals enabled. Nice and simple. All right, let's head on over to our plugin editor.cpp. Head over to the paint function. And, that's the wrong paint function. Response curve paint function. And if our analyzer is enabled, grab those paths and draw them. If should show FFT analysis. Do this. Here's where the paths are drawn. Put that right in there. All right, let's test it out. Oh, before we test it out, we should not, if we are, where's our timer callback for this guy? All right. If our analysis is turned off, don't do this stuff. All right. If we should show the analysis process, the FFT guys should, the path producers should produce the path. All right. Now we can go test it. All right, let's run some audio through our plugin and check out that button. All right, cool. That is working. Awesome. So analyzer enablement button is implemented. Implemented analyzer enablement button. We did that there and did it here. Cool. All right, the last tweak that I want to do, let's head on up to the top. We're going to head up to our drop rotary slider. I had said I wanted that text to be adjusted. All right, so let's do that right now. Okay, so right here, if we're enabled, use the black background. Otherwise, use a dark gray background. And then if we are enabled, use white text. Otherwise, use light gray text. All right, let's see what that looks like. Hey, awesome. All right, I'm very happy with that. Okay, cool. All right, let's make a commit of that. Tweaked button text when enabled or disabled. All right, that is the end of the tutorial. I am going to dial in the graphics a little bit more, but there you have it. That is how to build the simple EQ. Thanks for sticking with me to the end. We learned how to make this simple three-band equalizer with FFT Analyzer. If you liked what you experienced here, you can check out my course Project 11, where you will learn to build the Project 11 plugin from scratch. I also have a course that teaches C++ from scratch in the context of writing audio software. The focus there is on mentorship and not on video tutorials. Programming is learned by doing, not by watching. So for that, you're going to work your way through 10 projects. I'm going to review your code every step of the way via pull requests on GitHub and Bitbucket because that's what we use in the real world. 9 of them are pure C++ projects that will teach you the language fundamentals. The 10th project is a multimeter audio plugin written in JUCE, just like we used here. It features level meters, histograms, goniometers, correlation meters, buttons and combo boxes, threshold sliders, saving and loading the plugin state, and a little bit of the DSP. Basically what you experienced here, but with way more visual stuff being built. And you aren't watching me build it either, okay? You are building it on your own. I take on the role of your project manager. I set up a Jira board with all of the instructions because that's how companies manage projects in the real world. I assign you issues from that board. You tackle them. I review your work and either help you when you get stuck or I approve it and assign you something new. In the end, you'll have built the whole plugin from scratch without me writing a single line of code for you. You're going to do it all yourself. I'm just there when you need help. So it's a pretty cool experience. I've had a lot of people go through it. I've had a few people actually manage to land jobs at some pretty big audio companies. So check out the link in the description or by visiting www.programmingformusicians.com. Thank you again for tuning in. I am Chuck. I also go by the name MadCatMusic on Instagram and YouTube. Good luck on your coding journeys, and I will see you in the next project.